So, hello. We are back. This is our day 7, and day 7 we are starting from Python. So I said start from Python, and it is now day 7, and we are creating something in Python like linear algebra.py and experiments.py. So you can either set up in your own variable if you are using uh, anything like Linux. You can create your own VNV, which is virtual environment. Then you can go and activate that virtual environment, and you can then use pip. So then you can pip install NumPy. As for Arch users, there is already NumPy installed. As for PyEnv, you have to install it. But I am like not going to do it in my own workspace. Why? Because these are experiments and they can break your CPUs. And my CPU usage is exactly nearly 66, 76%, which is a lot when I'm not doing anything, just recording my stuff, and that's it, using two browser tabs, that's it. And it's a i3, so that works out. So I'll not be using my PC for now. We'll just do it in Google Colab. So I've created day 7 Python ML lab.ipnb, Jupyter file. As for why I'm not creating two files like linear algebra.py and experiment.py, we'll just segregate over here only. So for linear algebra, we'll just add a text file like linear algebra, and for experiment.py, we'll add the text file for the same. Now, since everything is correct, if you have installed pip install numpy, you can just run this sample code so that you can import that numpy as np and just print the numpy version, so that you can be now sure that numpy is properly installed and you are using it. It's all working. And then we'll now get to the math and linear algebras and all that. So let me hear something. I am audible. Everything works fine. Yeah. So let's start. So this is now phase 2, which is now linear algebra fundamentals and core ML primitives, which is everything in ML reduces to y is equals to x, and this is w. Oh, you must understand this deeply. All right, we will. So part 1 for this is now dot product. Why it matters? So a dot b is summation of ai bi, which is dot product. Now these are for vectors. All right. So this is the core of linear regression or neural network layers, similarity search and attention mechanism. Dot product is equals to weighted sum. This is a summation, and we are summing what? AI bi. All right. Now there is task A. So it says that create in linear algebra.py. So we'll first of all, segregate it using some sort of text which says uh, star. This is now linear algebra.py. This is my Jupyter file. That's why I'm doing this. Otherwise, you can just directly create, uh, using Newton or just touch. You can just create whatever the file name is over here, linear algebra and all that file, algebra.py. All right, you can do that. I'm not going to do that. So let's move on. We'll be using this for mostly all purposes. Now we are defining the dot product in Python using this function which says def dot. So let's do that. And the def dot will take two a and b. All right. So we say def, we'll define dot in Python, which will take a and b, two numbers. Now we are asserting something. First of all, use colon. Or now we are asserting something that is important. We are asserting that length A and length B is this. So now result is 0.0, and then we properly add this result. First of all, we have asserted, and We have to assert first. ASSERT. What are we doing with this? I don't know. A is equals to length b. So if it is not true, I think the assertion will be wrong and the process will get stopped right over here. I know the assert equilibrium or assert EQ in Rust. It is a macro, how it is used. As for Python, I've never used assert, so I don't know how it works. But in Rust, what happens if you assert something and it is wrong, process stops over there and you get a very beautiful error message saying left is equal to or not equal to type, or just there is some type errors, or it is definitely not equal, so something like that. And if it is equal and everything works fine, then you just get nothing. All right, if everything works fine, you get nothing. So we'll now say return. No, not return. We'll say result. RESULT. Result is equals to a float, which is 0.0. And then we'll run it in a for loop because we need a summation. We need a summation for all AI, BI. For I in range of length of A, we want a summation which says that result should now get appended by A as A's I element multiplied with B's I element. And after multiplication, whatever the result is, it will get appended to the variable result. All right. Now, we then, after calculating the result, we then return RETURN, return the result. All right. Now, this seems fine. This has been defined but not been used, so it works fine. It is like, yeah, everything is tick. And if we now send some A and B to this, we should get some really nice dot products. Now task 1b is, the important is no numpy inside this function. So we have not used numpy for this dot multiplication. So everything over here from range to length to, assigning A and B, calculating to the index of AI and BI, everything is now Pythonic. So everything has a Python object, numbers are now Pylong and everything like that. But NumPy does not use Python object. It is written in C. It just uses the Python interface to be called. Now we create our dot product in NumPy. So now we'll say we are importing NumPy as NP, as NP. Everything is correct. And then we'll say define the dot for not Python but NumPy. That will take A and B same as always. Now how it will calculate? It will just return, no loop, no nothing, just directly return return np dot of whatever this A and B is. So we are sort of calling a np dot, which is I guess method or a function, and then we are directly getting. So is there? Yeah, there was something documented. I want to see how it happens and how it is described. Not this. I want to see about this. Uh, so dot, it takes arrays like A array like and B also array like, and then out is none, which takes, and then any. So we define dot, which is a NP's sort of method or a function in a class. Dot A, B, and out is equals to none, then dot product of, damn it, shit. How did we got those suggestions? No, I want those suggestions. So NumPy We get NumPy, how to use and documentations and all that. It's all right. I want to see dot NumPy dot. Yeah. So if we send 3 and 4, we get 12 directly. Neither argument is complex, conjugated. So np dot dot, if it is 2j, 3j, 2j, 3j. So there are A and B, and we are multiplying them, I guess. Because it says dot product. So we get 13 plus 0j. Mm-hmm. Neither argument is complex conjugated. Then we get this. For 2D arrays, it is the matrix product. So if A is something like this, B is something like this, then np dot A and B gives us some array like 4, 1, 2, and 2. All right. Then if there is A something like np arrange, which we did yesterday, and then there is 3 cross 4, 5, 6. We are multiplying all them. And then there is a reshape which uses 3, 4, 5, 6 with commas. Now B is also 3, 4, 5, 6. Then we are taking some initial and ending from, oh, we are just reversing this, whatever this is. In what order? There's no order to it. So now this looks like reshape and 4, 5, 4, 6, 3. Then NP dot is something like AB. Ah, shit. I want to see this. NP dot looks something like 2, 3, and whatnot. The sum is this. All right. Out also takes the array type at the rate dot. Then this returns a array type at the rate object. Uh-huh. Dot a b and out none. Dot products of two arrays specifically. If both a and b are 1D array, it is inner product of vectors without complex conjugation. If both a and b are 2D arrays, it is a matrix multiplication, but using matmul, or a and at the rate b is preferred. If either a or b is 0D scalar, so 1D, 2D, and then 0D, which is scalar. It is equivalent to multiply, and using numpy dot multiply, which is a b, is a and then multiply b, is preferred. And if it is a ND array, which is nobody knows how many dimensions are there, and B is a 1D array, it is a sum product of the ocean. It is a sum product over the last axis of A and B. If A is a ND array and B is a MD array, so nobody knows what type of dimension both A and B have, where M is greater than or equal to 2. So it is this is either 2D or more than that, which is 3D or 4D. B is 3 more than 2D, so it is 3D, 4D, or equal to 2D. So it is now some product over the last axis, and A to the second shit. Hmm. Hmm. And A over the second last array, second last axis of the B. Now dot A B I J K and M. Sum is like A I J, then B K, and apostrophe. And what is this? Why is there colon in between them? It uses an optimized BLAS library when possible to see numpy dot lin alg, which is like linear algebra. And parameters like looks like a, which is array like first argument, b is also array like, which is second argument. Out is nd, like nd array. What is nd array? Which is optional. So output argument is, this must have exact kind, that would be returned. If it was not used in a particular, it must have the right type must be C contiguous, and its D type must be D type. That would be returned for dot A and B. Now this is a performance feature. Therefore, if these conditions are not met and exception is raised, instead of attempting to be flexible. Now returns is like, output is something like ND array, and returns the dot product of A and B. If A and B are both scalar and both 1D array, then the scalar is returned, otherwise an array would be returned. So there is a value error. See also all these example, I've seen them. So now we at least have a bit of idea. Like there can be three parameters, out of which the A and B should be array like, most probably. And there is then out parameter, for which mostly we have seen none. I don't know what it does, but we know there exists something like that. Out is none. So see, out is none. And yeah, it is the same thing that we have read already. Now we know a bit about it. All right, let's see B, and that's it. That's clearly it. This also works. Yeah, it works. Now we want to send some A and B. So this is test dot product. So it is asserting dot product for Python A and B, which is equal to 32. It is telling me. And now for NumPy, it is also equal to 32. But we want to see if anything is wrong right now. Oh, we shouldn't be copying and pasting it. We should just write it for our own benefit. Now we'll define test, test what? Test dot. So it will test the dot product. This is also a function which test our other two functions. Now 1, comma 2, comma 3. B is equal to 4, comma 5, comma 6. And we are asserting two things. First for dot Python and second for dot NumPy. There's a lot of noise outside. Let's go. Let's assert, first of all, for dot Python, dot dot Python. What we assert is A, we'll send A and we'll send B, and what we want is equal to 32. Right? Now we assert for dot NumPy. What it will do is it will also take, oh, it first of all makes the np dot array, out of A, and then it makes np dot array out of B, and that's what is getting sent. And now it should also be equal to 32. Now if we run it, yeah, it is correct. So assert also is a non-dramatic sort of function. Well, in Rust it is a macro, so in this I think it is a function or what, method. But why non-dramatic? Because it does not print anything if everything goes right. And if everything goes wrong or anything goes wrong, it will print. Like we make it 31 and we get some sort of error. Oh, we did it. Damn it. We didn't got any sort of errors. What is happening right now? What the hell? How about 3? At least give us some error, no? Why the hell wouldn't I get some errors? If assert fails, it stops. What stops? So let's try printing it. print. What we'll print is dot by the past, and then the value of it, which is dot python with a and b in it. And we have not added the f formatter, so let's add it. Let's try running it. We don't see the print statement. It means both of them have been dropped. Now we should see a print statement. We still don't see a, what the hell is going on. Shit. How about we run it first? So go over. Now try running it. You're not seeing anything. All right, all right, all right. Let's just say print I. Will this print anything? I want a message right now that we are not seeing. It is not. Shit. Shit. What is happening right now? This runs, this shows. So if we run print high, it would show us print high. Let's run print and then high. Yeah, there's print high. So let's cut it. Rolex. I code a new line. This run on. It runs. You don't see any. Now run. It runs. Run all. Still runs, and we are not still seeing anything. So let's go down. Now run all. Runs. We are still not seeing anything over here. So did we do something wrong? Did we do something wrong? Like, should I not intend or indent anything? Should we not use any kind of indentation? Is that what you want? We'll do that. But then A and B is not defined now. At least give us some errors. So we got some errors. All right. So indentation is important over here. Ah, oh, I know. I'm such a stupid. What's happening right here is we are not calling this dot function, all right? So obviously, shit, I'm stupid. I can be stupid sometime, but it's all right. Now no errors, it's fine, it's good for us. Now we go here and we call this function, which is called test and dot. Yeah, I sometimes forget that this is Python. Now we are getting some errors. Why are we getting error? Dot Python passed. So first of all, we got this. And second of all, there is assertion error because of this. So let's call it 2 and let's go. So yeah, no errors, no nothing. Everything works fine. Everything is fine. So let's go. We'll copy this and we'll make the same thing because we also want to see the response, but not a dot response, but numpy is dot response. So it is important. And even py numpy passed with what? And second thing I want to see is numpy. If we just send a and b without making them a numpy array, what will happen? Will it just affect the speed of it, or will it just not work at all? I will see that too. So Yeah, NumPy passed, and it might have taken a bit more time than it should have, because it is now taking directly A, which is a Pythonic object, B, again Pythonic object, and we are not creating a NumPy array for it. If we create the NumPy array, I think it will be more optimized and more fast, because NumPy arrays are better. That's what we have learned for past 6 days, I guess. This is our 7th day. So yes, for past 6 days we have been learning that only. So just use NumPy array, which will be faster, quicker, easier to compute, and all that. Now, I think everything is set. We get the same response, no change at all. So .numpy, same thing. .python, same thing. Now we don't need you, so get lost. Yeah, everything is fine. So run this. If assert fails, it stops. If it doesn't, it doesn't. Like, what was the assert? So if I make the assert wrong, it will obviously fail. And now we'll see the assertion error. So yeah, why earlier we were not seeing the assertion error? Because we were not even calling this function, no? So after we called this function, we got the assertion error. That was important. So now the assertion error looks something like this in Python. It says test dot, which is this, right? So after 10th line, we are getting back to the 7th line. So because of 10th line, we ran this function, which was test dot, and in this we got stuck in 7th line. That's what it's telling me using that arrow. Then we'll go to the 7th line and see if there is any error to it. It doesn't explain error, so good for you. Now we see that, well, we noticed that there is only 3, but it should be 32. So we go back to line 7. We see, yeah, there is 3, should be 32. That's what it's trying to tell me. And oh, now we made it 33. So we should see again in 7th line, it says we have some error. I see that assert is correct, .numpy is correct, np.array is correct. We are passing A, which is also correct. We are using comma, which is correct. We are separating it, the B, which is now correct. What could be wrong is this 33, or sometimes equal to, where we just use sort of 1 equal to and forget this. So it, instead of calculating the left and right, instead of checking that, we are trying to what is that called? We are trying to give it a value, but there is nothing to take over here. It just equates. Check the equivalent. So that, therefore, this is important. We have done sort of 3 errors, intentionally and unintentionally both. First one was unintentionally, obviously. I forgot that after defining a function, you have to call it separately. So now we know we can do that stupid mistake. Well, I can do that. Now part 2, there's a matrix multiplication, matrix vector multiplication. So now again, why this equation that we saw earlier, we are seeing it again, and it's telling us why this matters. So matrix vector multiply also looks something like this, whereas X is a data set, which is row or samples, and W is parameters, Y is prediction. So when we multiply the data set with parameters, we get the prediction. Now this is linear regression. What was this? This was linear algebra. We were doing dot product. Now we are taking data sets and multiplying with parameters, and we get a prediction. And that's what we call a linear regression. Now this is important. This is quite important. So we'll do that. We'll create a code, which is our task 2, which is manual matrix multiplication vector. So first of all, before doing all that, we make a comment about manual matrix vector. All right, then we define it, and before defining, now let's first of all call it. But first, before calling it, we should have at least a matrix and a vector, which is over here. Let's define it. A mat vec in Python, not NumPy right now. This is Python object. Inside that, we'll send a matrix. So why is it showing me capital A? Because matrix of size is written in sort of capital words mostly in maths. We are sending it matrix and vectors. All right. Then we say something like result is an empty array. Where is array? Yeah. RESULT. Result is an empty array. Yeah. And now we are running it in a loop. So for rows in matrix, we are running a loop which says result dot append. So append is a method that we use for appending things to an array in Python, because everything is a Python object and you have to use Pythonic methods to do what you want to do. VCTOR. So inside, result, again, result is wrong. RESULT, result dot append. So append is a method which takes something and appends to the result, which is an array right now. What we are trying to append is whatever the result of dot product from Python is. Before doing that, we have to send the row, which is not defined right now. So therefore, I am guessing that there's an error sort of, yellow lines. And yeah, it is also there because the spelling is mistake. So this is now correct. Row in matrix. So we have to send the row and the vector as for the same, which is over here, vector. So we run a loop on. So for mat vec Python, this is a function. We get matrix and a vector. All right. Now we create an empty result array and we run a for loop on matrix. We are not even touching vector right now. We run a for loop on matrix, and for matrix we get rows first of all, not column wise. We are getting row wise. So for first row, let's say we are appending it in using dot product, the result of the row and the vector. We append it in result, and for the, let's say, second row, we get the second result. We append it into result array. That's what we are doing. Now, to call this madvec Python function, we have to need two things, which is matrix and a vector. That's what we are defining it over here. So it says test it. So to test it, we'll make something like test and this madvec Python. All right, we'll create that and testing testing what manual 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 matrix vector. All right, this is done. Testing. Now we define something like test vec. Yeah, test matvec. And inside that, we'll say there's a matrix, matrix, which not np dot matrix, sorry, it is just a matrix. And we say it is looking something like this. We have a column which has value. We have a row which has well, two columns, 1 and 2, the value of it. We have second row which is again two columns, so 3 and 4 are the values. As for the vector, what sort of vector it is? VECTOR, we are sending the vector which is 5 and 6, let's say. Now what do we expect when we send this vector and matrix to a function matvec Python? We send when we send matrix and vector, We expect what? We expect a result. So to do that, we have to create a result. But we have done a mistake over here. We appended it but did not return this result for this function. So return the result array. Now we return the result array. Now if we define this metVec function with these metrics and vector in place, we should get a return result array. So we have to define a array which should look like, expected. We'll say expected expected, or shall we call it result? Result, but it is a different result. All right, result. Result from mat with Python and sending this matrix. I will get a result and we print it. First of all, just print it. Print this result. Print this result. It didn't print anything because again we did not call this whole test malware function. It requires nothing, runs solely. We are getting an error. Obviously, just without error. Something is first of all, append a comma. Do we still get an error? Yeah, it is a name error. Why? It says test metVec and then it says this result. Right. So name metVec Python is not defined. But we defined, we did not, might have, yeah, we did not run this. So for this to work, it should run this metVec. Now everything should run smoothly. Yeah. So we were expecting this 17 and 39. We got the 17 and 39. So instead of printing the result, we can also assert assert. That's how we use it, I guess. We give it a result and we equate it 17 and 39. And even if we don't print it, that's what we should get. But if we get something like 16, or let's say we asserted something wrong, then we get something like assertion error. So our assertion was wrong, or whatever the result we are getting is wrong. Now how this calculation is working, that's what we are saying over this slide. So it says we take this first row, first column thing, that is 1. You multiply it with this 5. As for the second column, first row, 2, we do that with 6. We are multiplying it. That's how we resolve this matrix and vector. Multiply. And then for 3, we are multiplying it with 5. And for 4, we are multiplying it with 6. I think I might need to revisit my matrix and vectors and determinants chapter. So I will go through it. For now, let's try to understand how it's all working. We have seen this. That's how we calculate. This is 2 by 2 matrix. The vector is 1 by 2. So if 2 by 2 gets multiplied by 2 by 1, no, it's 2 by 1. This is 2 by 2, which is 2 cross 2, and this is 2 by 1. So when we multiply both of them with a dot product, what we expect is a matrix which is resultant, which will be of 2 rows and 1 column. That is this. This is what we expected. How we get this is, first of all, we multiply this 1 1 with 1 1 of another matrix, this 1 2 with the 1 2 of another matrix. As for this one also, it also gets multiplied, but forms the second element. This multiplying will form a first element which will be 17 after adding it, and then we do this operation with the 3 4 multiplied with 5 6, adding them we create a second element. If it would have been something more robust like 5 6 7 8, let's say, then the expectation would have been something else. So let's do that, but before doing that we have to use square brackets and then comma. Then let's say we have 7 and what, 8. Let's use comma. Let's enter it so that we can see it more appropriately. First of all, there is a type error, which is comma. Still a type error. What is it? I don't see. And type error was not due to this. I am guessing. Type error is because of this. It says result. Unsupported operand type for plus equal to float and list. So we have created a result which will be of this type. So I think therefore we are not able to get a 2D result. We are expecting a 2 by 2 result, which will be a like square matrix. But the result looks nothing like that. For that, we have to create a loop for I and for j, I think. Then we'll be able to get what we were expecting. For now, let's not do this. Let's be satisfied with what we actually did. Now assertion is, why is assertion wrong here? Uh, Length of A and B, right? So I think we might need to erase these commas. Everything works fine. Yeah. Now there is a task to be. So this task is done. So now we have created manual matrix vector using Python. Now we'll do that using NumPy. Let's do this. Take a text, paste that text, escape from this. And then instead of making it in a different code block, let's keep it in the same block so that it looks nice. Does look nice, sort of. We run it together, because if we run this code block and did not run this, we'll see nothing. If we run this code block without running this, we might see an error because it does not know anything like matback. And as soon as we run this whole column, everything is good and fine. Now, before doing this, we have to generate a new text which will say manual matrix vector, which is good, but using NumPy. That will be the change. For this NUM, then PY NumPy. Over here, it's just Python. PY Python. Now let's start by defining again the matback. Oh, it looks like This is 2a. This is 2b. Yeah, so I was expecting to see something like NumPy and all that, but I saw something like Python. Now that got me confused. Now for NumPy, how do we do that? We return matrix into vector. That's how we've defined it. All right, because it is 1D. Uh, then we test it using this. We send directly array, and this multiplication, which is NumPy's type multiplication, and then we send another array. That's how we test it. Now it looks very compact and it works efficiently as well. So let's define it. Diff using mat vec, not Python, but numpy. Numpy. Inside that, we'll send it a matrix and a vector, and we are expecting a return of 1D array, which will be multiplication of matrix and vector. All right, seems nice. Now we have to call this function matvec numpy. We'll call it in. We'll call it in a test. So we'll define a test for this. We defined test matvec pi. We have to create a pi for this. Pi. Let's say pi. Same function. Now over here also we'll say something like this. Before that, we'll just create a test, and it takes nothing, but it gives you something. And like always, not always, but I'll just directly call this function without making it, because we always forget that we have to call this function. Now starts defining this function. So instead of directly sending this matrix and vector directly through NP array, that we can do, it's not a problem. It looks more compact, but looks more confusing too. So instead of sending the whole element like this, we'll first of all create a matrix and array. But again, that will be, Pythonic object. But that's what it's taking, no? This is also Pythonic object, but after going through np.array process and all that, it becomes normal. So let's do that over here. Let's do that by what's called forming a matrix, which will not NP matrix. Yeah, this matrix. So now we have a matrix which is np dot array. So we've learned something new. To create a numpy array and call it a matrix, we can do this, and then I hope we can do the same for vector, but we'll do it now by our own hands. So we'll say np dot array. It will take a circular parenthesis. Inside that, it will have a square brackets. Inside that, element A, element B. I think this works. Now what we'll do is we'll say something like, now return, not return. Why do we want return? We want result. So we'll say result is equals to matvec was the function. So matvec numpy, matvec numpy. Inside that we'll send our own matrix, and we will send our own vector. We'll say vector. Vector. All right. And then we should get a result from this using matrix and vector. That now we should print whatever this result is, and assert. Oh, this assert looks different now, but all right. Now, as soon as we press enter, we get to see 17 and 39. Looks different because it is only separated by space, not by comma, like here. There is no decimal place, it's gone. We don't even need this for now. What we are seeing is the print of the result, which in itself looks different. What if we directly call this? What happens then? 2 minutes, give me 2 minutes. Yeah. So outside of this function, what if it, instead of calling, test and all that, what if we directly say that there is a numpy array, multiply it with another numpy array, and well, will it show something, or we have to, type print? Well, it showed us that it is a array which is of type 17 and 39. Now, this looks fine. This is good. Everything is working. And we did not use this matback numpy over here because it returned matrix multiplied by vector. We are directly doing it. This is a matrix for us. This is a vector for us. And we are directly multiplying it using @. So we didn't use this function, so we didn't need it. We'll say this as a direct, you know, dot we are ODUCT using numpy. No need to create a definition or whatever function. You can directly do this, but you know, this is not a function, so this is not, we cannot call it again and again, and it is very manual work. No, manual is this, doing this is manual, doing this is manual, creating this is manual, but it is also simplified. So just for the sake of simplicity, we'll do all these lines instead of just doing this single line. Well, that's how we work. Now part 3 is this performance benchmark. So now comes the second program. So first program was all this, which was linear algebra.py. Instead of creating a pointer, it is not a pointer. What is this? We call it something like bullet point. Yeah. Instead of creating a bullet point, we should be creating a whole, yeah, heading. Now let's create another heading because we will need it, because we will be benchmarking it. So now we should have something like experiment.py. There is a spelling mistake. How could it not be a spelling mistake? Experiment.py. All right, we now have experiment.py. We have a benchmark setup which looks something like this. We'll run it and we must note down which is good, which is bad, which takes more time, which takes less time. All right. So let's start by importing first of all time, because we are benchmarking now. Second of all, numpy, because that's what we are benchmarking. And third of all, we are directly, we have a sort of a library called linear algebra, and from that we are directly calling or importing something like .python and oh shit, it is our own library or sort of Python file that we created distinctly on our computers, but all right, we did not, so sorry for that, but we'll do this. All right, we'll do this because now it seems interesting and it didn't need much of a compute and seemed safe, so we'll do this. We'll copy all these functions and we'll do it. First of all, try to make it more compact. So this is a .python. It is NumPy. So let's take it in one. Why should we make another block for this specifically? Let's take it to the top. That's what we do always. Give it some space. And then we are testing the dot by sending both of them. This looks like really nice program. Compact. Oh, sorry. Shit. We. Hmm. Now I'll just copy and paste if I want to create something like linear algebra.py. This is manual vector Python. This is a part of linear algebra.py. We'll do that too. It shows some error using matpec. Why? Because there's nothing as matpec. There's matpec.python now, like underscore Python. So create a Python. Now there shouldn't be any errors. If we try to run it all for the last time before creating new files, yeah, there is no error. See that? And we are happy after seeing that. Now we'll create a experiment.py. We'll not import this thing because I don't think that's how the IPA works. This is a Jupyter notebook. So if we run it all, it runs. We don't need to import this. So we'll keep it, but keep this commented out. Instead of copying and pasting, we'll write it down. So that way we can have a more time to have some discussion on what we are doing. It also gives us time to think. So when you are importing, first of all, it also gives us a time to make some typos and then improve those typos. So yeah, everything has a upside and a downside. Now we'll write this in NEAR algebra ALG VRA. It says import dot. See, we had a yellow squiggly line. Dot find. All right, and we'll just comment this whole lamp thing out. You just comment it out. Now it works fine. No errors. If you don't comment it out, we get an error. I guess so. Module not found error because we did not create a module named after that. Because yeah. Collab or this Jupyter notebook has upside, which is you don't have to create multiple files and you don't have to edit multiple times. So that is the upside. Downside is that nothing realistic. I don't see much of a downside to using this Jupyter notebook because it is very easy, helpful, and most importantly, it is remote. So if any harm is done, it is not done to you know, my laptop, which is important. So we created a size which is n of 1,000,000, and then we have a list which has an array multiplied by size. Is it an array? Is it a list? Let's go and find out because we are multiplying it with our size. Ah, what is it? Not 8, but a star. And now size. Let's go up. I don't want to see the error. And now create a B list. I'll give it a 2. It's not 2. We are multiplying it with the size, which is nearly a million. So we get a 2 million. 1 million and 2 million. Nice numbers. Now for NumPy, we are directly creating np.ones and size. Np, now what it does, we have only seen it for the first time. So I've never seen this np.ones in my life. So we are doing this for the first time now. This is something new for us. So congrats. Now we are learning something new. Now we are creating B for NumPy, BNP. It has np dot ones. It takes the size and multiply it by 2 because that's what we want. So what I'm guessing from writing these two lines, I think the np dot ones gets a list or a array of 1 multiplied by the size, and to get the array of the same size, but instead of 1 we should get something like 2, so we can directly multiply it to that array and we get a new array with size 2, or well, not size 2 but elements as 2. That's what we are multiplying. Now we are defining Python loops and all that. Now that's important. All right, let's create a Python loop and then we'll create a NumPy loop. Let's do that. uh, Python loop, and then let's create a NumPy loop, umpy loop, and in Python loop we will say something like the start. That's what we are doing for the past, I don't know, 6 days. We use time and inside that we use perf counter because that's more scientific, and all the upsides of using perf counter. Not pref because it's not pref but perf, so I call it perf counter. I don't know the real pronunciation of that, but dot in Python, and we are doing that dot Python, dot a list and b list, which we have created earlier in the same program. Over here, a list and b list. All right. I don't think there's any error to it. Now we are calculating the time, so and is also like this, and yeah. So I press the tab and it auto completed. So end is also time dot perf counter, and we are then printing the time it took using end minus start. That's how we do it. That's how it did it. What else we can do is we can directly say that whole time, and instead of getting time dot perf, you can also do something like start. You can directly minus the start and then print the time. That's also how we did it uh, in earlier lessons. For now, let's keep it more simple, more simplified. Uh, now we'll create a NumPy loop. So we'll say start is again the same, which is time per counter. We are using dot NumPy as a function now, and we are passing a and b like this, and b and p that we have already declared. Now let's give it a end time, which is time. Yeah, so I see all the nice things that we need. How about I write it this time? So we set time dot perf counter, TR, for COUNTER, per counter. Then we print. Now printing is nothing rocket science, so we'll just print it. Then we'll run the benchmark dot, which is this function. Now, after defining this function, everything should work out of the box, and it works. So Python loop took this much time, and NumPy loop took this much time. So interesting thing to see. As for if we try to run it all, what's the result? Same thing. Nice. So it's nice. And after doing that, that's what it wanted. We'll copy this timing, but you must write down. In notes, I must write down why NumPy is faster. Something like C backend, SIMD vectorization, and contiguous memory. Contiguous memory is side by side storing uh, every numbers in an array side by side, so that we can directly use the CPU caching and all that. Now, fewer Python interpreter overhead cells because it is written in C and it converts everything in C. When Python loop is acceptable, when the vector is very small or data set is very small, then we are debugging something and custom logic per element. Then we can use Python loop. Well, it's acceptable. Now, part 4, it says conceptual understanding. Before we move to gradient descent, you must understand dot product is weighted sum, matrix vector is batched weight sum, and ML, which is repeated matrix multiplication. What is that? All right, your test. Do not skip. All right, I'll answer these. I'll try to answer these. First, it asks me, why does NumPy require contiguous memory to achieve SIMD acceleration? Hmm. One page GO G G memory has many upsides like CPU, CHK, CHIG, and SIND acceleration due to the vectorized data set form. I think I have answered it enough. Caching spelling is correct. Not chasing, it's caching. C is CACHING, caching. SIMD. Well, this is correct. What else are you suggesting me? Sims, no Sims. It's SIMD. Vectorized, it is correct. Or Z, I guess. Doesn't matter. Now, second question. Do something like conceptual, which is if vectors are length 10, why might Python loops be faster than NumPy? Because going nearly small SMALL data sets, it doesn't make much of a difference. It is because of the small data set. Only NEARLY, and because VCAUS, because POESNT doesn't make sense, right? And the reason why is because it's small. So the time it takes is also small. Let's do what? Let's change the data set from million to 1. Then let's see how much time it took. So it took nearly approx 2 seconds, and this also took approx 2 seconds. Well, not 2 seconds. It's something like e to the oh damn it. Still, NumPy loop took less seconds. But does it matter if both are in tenth of microseconds or something like that? How about just 1,000? What is it? Ah, I will do that. Let's now create the whole number, but not run it. Ah, now we see it's still e to the power minus. So e is like base 10 and to the power minus 5. And this is something like minus 4. 4.6 e to the power minus 4, and this is 6. All right. Uh, After correcting everything, this looks something nice. Hmm. NumPy is always a tenth faster than a Python. Now, third prediction: what happens if you pass Python list directly into .numpy without converting to array? .numpy. What is .numpy? .numpy. Yeah, .numpy is this. NumPy's method, and it takes array using that is created using np, which is NumPy library, and if it directly takes the Python object, then it is not contiguous, and you are still using the Python object and pylongs. You can't take much advantage of NumPy because we still have have what uh, Python objects and numbers are in form of what? Pylon. So NumPy takes its time to convert it and then use it. So it sort of slows it down instead. There are multiple spelling mistakes, but we don't care. We don't care. We literally don't care. It's for, not dollar. All right. Now implementation. Modify .python to use zip instead of indexing. Write the new function. So let's first of all, copy the .python. And it tells me, well, it sort of told me to create something like this. So we'll do that. We'll try doing that. So this is a new function. We'll add z to it, not zip, just z. And this is a new function, z.python. Now what? To use zip. So how to use zip? I've never used zip, but I've seen it somewhere. We've seen it somewhere, didn't we? Yes, we did see zip somewhere. Where did we see zip? Not here. Not here. Then where? All right. I don't know how to do this, but mhm. Instead of taking directly matrix, how about we zip it? What happens? Not here, not here, sorry. Not here. We do it over here instead. Uh-huh. So our question is, first of all, how to use it? And where should we use it? Where should we use the zip? Enter. How to use zip and where? That's our question. Well, that was our task, first of all, but still, let's paste this instead. And I think I'll create something like funny, but not funny at all because we are ignorant. That's why it's not funny. Good. Now we sharpen. The benchmark difference is 32 times faster. NumPy is exactly what we expected for 1 million elements. And that confirms the proper measurement. And now let's audit your answer precisely. Evaluation, your answer CPU caching SAMD due to vectorized dataset form. Correction, correct but incomplete. That's what it always tells me. So SIMD instruction operates on fixed bit registers like 256-bit AVX, 256 bits. So if we divide it by 8, we get how many bytes? Uh, if there is a 256 and we divide it by 8, let's do that. 256 divided by 8. We get 32 bytes. So it has, well, I've heard that it has something like 64 byte registers, but over here we are seeing only 32 byte AVX. So let's take it as a truth. To load 4 to 8 floats at once, memory must be sequential. So continuous memory allows efficient cache line prefetching. That's what I told. And single wide, that's what I told over here with CPU caching. That's what it does. It takes, uh, it fetches the whole 8 elements directly in the first cache. No, in the first sort of, pull request or something like that, it gets all the 8 elements and it operates on first element. Until then, the rest of the 7 elements are cached, or it can just use all these 8 elements together because it is CPU and it's powerful. So it says to load 4 to 8 floats at once, memory must be sequential. To load 4 to 8 floats at once, memory must be sequential. Yes, that's what NumPy array does. Contiguous memory allows efficient cache lining prefetching. Yes. Single wide load instructions. Yes. No pointer chasing like Python objects. Yes. Python list stores pointers, which creates a scattered heap object. No vectorized load possible. So you identified the caching plus SIMD. Good. Next time, explicitly mention Python list stores pointers. You know that. You all know that. Because it is a Python object, and the list stores the pointer, and the pointer points toward a pi long, which is not even a number. It is a pi long, which is sort of a number, but a Python object number. So it is long, it is bulky and all that. A NumPy stores raw contiguous numeric buffers, and that is the key system distinction. Now you said it doesn't matter much. Well, I shouldn't have said that. I am sorry. It says it is too shallow. Well, can I do? Now the real reason is NumPy has overheads, which is like function call overhead and argument validation, D-type checking, and possible array conversions. So for small vectors like 5 to 20 size, which is of size 5 to 20, the constant overhead of NumPy may exceed the actual compute time. Now this is a classic, like 0n versus 0n. A different constant factors. So n is different for all of them. Or I guess O is different. What is constant factors between them? Now third is parsing Python list to np dot. Your answer says NumPy takes time to convert and slow down. Mostly correct, but refined will be something like if you pass a list, then np dot will 1, 2, 3, 4, 5, 6 internally convert them to array first. That conversion take something like allocate new memory, copies data, impers to D type. Now that allocation cost dominates for small vectors, but not for large vectors. A correct pipeline, zero copy matters. The zip implementation is incorrect, I guess. Yeah, this is incorrect syntax. Incorrect usage of zip. What zip actually does. So we zip A and B, so pair elements. So you don't need indices like A0, B0, A1, B1, like in matrix 2. Correct implementation would be something like mhm, uh, A and B. So first line is correct, or like the same, second line is same. And for instead of sending just I, we are sending X and Y in zip for A and B. And result is then stored like X and Y. Now this is interesting. X, X and Y. Instead of getting range and then length of A, oh damn it. Dot Python, dot Python, dot Python, where's dot Python? Over here. Oh damn it. It runs so primitively, like we are using range, which is a Python object. Then we are using length, which is again a Python object. And we are using that so that we can run for how many times? As long as the A has a length. Well, zip is sort of shortened way of telling all these things. I noticed because how many brackets were there? Zip or zippo, and it uses a parenthesis again. Is it called a parenthesis or circular bracket? What is it? Ah, a good question, but at a wrong time. Now we have to say A and B. A and B. So it takes both A and B instead of I as X and Y. So what it does is it pairs element and you don't need indices, which is indexes, but plural. So now this is correct syntax and incorrect use of zip. This is corrected version. Corrected version looks something like this. How about running it? I shouldn't see any errors. We are not seeing any errors. It is cleaner. It is efficient. It is good. How about we just copy it and directly paste it? I think there is some indentation problem, but it is not telling us right now. It might. Let's see. This is cleaner, more Pythonic, slightly faster than indexing. No repeated list lookups. Yeah. Now new test, which is deeper. So answer carefully. I will try to. Y is for X and Y in zip AB generally faster than indexing with range? Well, first of all, zip is just one Python object, but range is one, length is another Python object. So there are first of all two Python objects. Then we are running A and B, and inside the loop, we are fetching AI and BI and doing some operation with that. But with zip, we can directly fetch, because of zip sort of what it does. It pairs element and you don't need indices. So let's copy this, copy this. Let's go at the top and get some three, right here, three WCs. Mm-hmm. You paste it. Now we know it pairs element, you don't need indices. So that's how we use it. How about you go to the top? Yes. So it directly gets X and Y from each A and B directly, and we can directly do an operation on X and Y instead of calling all that range, length, and A. As for interpreter behavior, I don't know. On today, we are learning quite a lot of new things, which is good, which is good. Because for the past 6 days in Python, there was not much of a project progress that we could see. Now we did. Uh, for X and Y in zip, AB generally faster than index with why? Because what I can think of is instead of using two Python object function like range and length, we directly use a single function zip. And next thing we know about this is directly range and length because CA. Now, next thing we know about this function, which is function zip, is it pairs element and we don't need indexes. It pairs element and and we don't need indexes. So don't do we don't do what? We don't do A, I, and B, I. We instead go directly by X and Y, which is good. Well, it didn't need my remark, but let's do it for the sake of personality. But ChatGPT also knows who is it dealing with. Now, if numpy arrays are contiguous, what happens when you slice like this? So if numpy arrays are contiguous, which means side by side, side by side, side by side, what happens when you slice it like this? Uh, we have x, which is numpy array. Then we are saying, you know, first element, whatever, then second element, whatever. Not second element, but what is this? End element is whatever. This is for sorting, We can do one for, normal. We can do -1 for reverse. What is this 2? Are we multiplying by 2? Are we doing what with 2? Is y still contiguous? Well, I think so. What does that imply for performance? Well, I now don't think so because there's another question like, what does it imply for performance? I don't know. And what are we doing over here? So let's just ask it because this is new for us. What's happening over here? Let's paste it. I don't know. Uh, and before that, I guess y is contiguous. I guess no. So I guess something and I say I don't know, and let's move on. As for contiguous, let's change the spelling. Now third. Oh shit, I pressed the enter. So there was third and fourth question. Shit. So run 10 times print average time and use time.perf counter, write only the benchmark function. And the prediction is which is faster and why. np.ab or ab and then sum. Obviously np.ab. Assume a and b are numpy arrays. Still, sum is written in something like C Python, whereas np dot is, so let's say this is faster because it uses numpy, whereas whatever this is slower because it uses sum, which is written in C Python. That's what I know. C Python. Okay. First of all, read all these answers. So let's read it. First is, why is it faster than indexing? Your answer direction is partially correct, but the real reason is deeper at interpreter level. So let's read it out. So it says what happens in indexing version. So for this, what happens is each iteration does a length a, which evaluate once, fine. Then range for produces iterators, which is fine. Now for I, which is the I over here. For I, we load a, we call a and get items I. We load b, we call b, get items I. We multiply and then add. Now, two list indexing operation per iteration. Yeah, so we are indexing two lists A and B simultaneously and then doing some operations on it. Two list indexing operations per iteration. Now, each indexing operation, which is bound check, method dispatch, pointer dereference, so it all adds up. Now, what happens in Z version? Zip version, not Z version. So zip version, what happens? So zip creates an iterator over both lists. So there are lists like A and B, iterators over both directly. Now each iteration retrieves next element from each list directly. No explicit index and no repeated get items. So we remove two index operations, two bound check, two repeated attribute lookups. Now that is why it is faster. Key principle is reducing interpreter level operation improves the performance. Another important one, the second, which is y is equals to x and whatever this is, contiguous. You said y is contiguous, I guess. No, I don't know. Correct instinct. Well, it was instinct from answering lots and lots of questions. I can see a question and try to figure out if it is correct or incorrect. And examiners have gotten used to that, and they create some different sort of questions which, well, simply doesn't signify whether this question is correct or not. But that's what examiner does, not ChatGPT. So it's easier to guess. So the answer is the let's reason. So what is happening? So XP is creating ones, which is like 10 sort of 10 elementary list containing of 10 times. Now what is Y trying to do? This means take every second element. Oh, so that what it meant. So that's what it meant. It's good. It's fine. So original memory is like x1 to x9, which is 10 elements. Now view it like something like this: 0, 2, 4, 6, 8. But these are not stored consecutively in memory. They are spaced. And are these pointers? I think so. Now these are not stored consecutively in memory. They are spaced. Internally, NumPy creates a view with stride is equals to 2 into element size. So stride is like steps. You will take each step with multiply by 2 into the element size. So if element size is 10, if element size is whatever, you multiply it by 2. And this means no copy but not contiguous. What does this imply? So SIMD prefer contiguous blocks, and when data is strided, which means you have to take steps carefully, CPU cannot load large chunks efficiently. Vectorization becomes less efficient, and some operations may fall back to slower loops. So performance may degrade. Important ML system insight. Contiguous memory is equals to peak performance, and strided memory, which is potential slowdown, and copying to make contiguous memory cost but faster compute. Now, framework like PyTorch often call contiguous for this reason. So if we use something like PyTorch, we would have to, call contiguous every time, most of the time. Well, we haven't used PyTorch, so all right. Now you must answer now. Question 2, which is revised. Why does strided memory reduces SIMD efficiency? We know because strided memory is potential slowdown. And why does it do that? Why does it do that? Because CPU cannot load large chunks efficiently. Vectorization becomes less efficient. Some operation may fall back to slower loops. So performance may degrade. Let's remember it. CPU, when we do something like strided memory or something like that, where we are taking 2 steps forward or directly 3 steps forward each time. So what happens then is SIMD prefers contiguous blocks, but now it is not. So CPU cannot load large chunks efficiently, first of all. Yeah, good. This point is now good. Vectorization becomes less efficient. I don't know what that means, but I know vectorization speeds up the process of calculation. But since now it is not vectorized, so calculation is now taking more time. And then some operations may fall back to a slower loop. So important ML insight, whatever this is, I don't need that. Explain in terms of CPU load instructions. CPU load cannot cache effectively, and vectorization becomes less efficient. So CPU cannot load large chunks efficiently. CPU cannot load large chunks efficiently. CPU cannot load large chunks efficiently. There's a large chunk, CPU cannot load it efficiently. There's a large chunk of memory and CPU can't load it efficiently. Now vectorization becomes less efficient. So some operations may fall back to a slower loop. So performance may degrade. Now important ML system insight is CPU, I don't need that. Now, which is faster? But I must explain these now. So CPU loading, large chunks of data sets becomes inefficient, and vectorized calculation or vectorized model, vectorization becomes less efficient. CPU cannot load large chunks efficiently. Operations may fall back to slower loops. And I sort of answered the third one, which is correct analysis. NP dot is faster because NumPy, and A cross B, which is A multiplied B, and then we are creating the sum, is slower because of sum is C Python. Now, this is wrong. Why? Because sum here is NumPy's method, not Python's built-in sum. Oh, now this is shocking. If A and B are NumPy arrays, and A multiplied by B, which is NumPy U function, which is vectorized and C backend, whereas sum, which is NumPy reduction, which is C backend. So both side uses C, not Python loops. The real difference is case one, the dot internally calls optimized BLAS routine, BLAS routine. BLAS routine. So what is that? We need to know something about BLAS routine. Now, no intermediate arrays, single fused loop often uses SIMD plus cache blocking. Now, case 2 is this sum wala function. We are multiplying A and B as an array and we are creating sum. So it creates a temporary array which looks like this, which is temp is equals to A multiplied B. Now this allocates memory, right, n element and all that, which is step 1. Now step 2 is loop again to sum, and then what? So this performs 2 memory passes, 1 allocation and 1 extra memory write. So memory bandwidth becomes the bottleneck. All right. So now this is more interesting. Correct answer would be that np.a and b is faster because it avoids allocating intermediate array. It fuses multiply plus accumulate. It may use optimized BLAS kernel. It reduces memory traffic. In numerical computing, memory movement often costs more than arithmetic. Alright, so memory movement often costs more than arithmetic. This is the real system level insight. Now answer this precisely. Why is memory bandwidth often the bottleneck in numerical computing rather than arithmetic operation? Why is memory bandwidth often the bottleneck in numerical computing rather than arithmetic operation? Because CPU does these operating operations which are far faster than any sort of numerical computing that memory bandwidth can even operate on. It is not even remotely close. Like memory bandwidth is, RAM speed, whereas CPU speed is something. Let's ask a AI, not ChatGPT, but a different AI, just for the sake of newer context. Not this. Let's not pass this. I want to ask, the the comparison between RAM speed and CPU speed. So these are related but distinct specs. Here's how they interact. So CPU supported memory speed means the speed listed in CPU specs, which is Intel i5, let's say, 10600K supporting DDR4, which is 2666 megahertz, is the native or base speed. So CPU officially supports without overclocking, not a hard ceiling. In practice, CPU can often run RAM at significantly higher speeds. What actually determines your RAM speed? Uh, three components are involved. So CPU, which sets the native baseline speed, motherboard, which determines the actual overclocking ceiling. Example, Z490 board can support up to 4600, which is like double. Now RAM, which is rated for its maximum speed, like 3200 megahertz. So XMP or overclocking. When you first install RAM, it defaults to a slow JEDEC base speed, usually 2133 megahertz, regardless of what it's rated for. You need to enable XMP in BIOS to run it at its rated speed. Now, this is technically overclocking, but it's standard practice and generally very stable. Does mismatched speed causes harm? No. Running RAM faster than CPU's native spec via XMP on a supported motherboard does not damage your system. The risk is mainly stability, which is rare with popular kits on popular boards. So CPU versus RAM speed. The bigger picture is CPU operates at far higher frequencies than RAM, and RAM is connected via memory bus, which acts as a bandwidth bottleneck. This is why a cache memory exists to bridge the gap between CPU and RAM. I want numerical data of what is the CPU speed and what is the RAM speed. I want numbers like what is the CPU speed and RAM speed. Well, I got some numbers, but not that interesting. But let's see. Does it give us something like? Hmm. So it ranges between 3 gigahertz and 5 gigahertz. Damn. And the RAMs, well, they're running on megahertz. Well, good enough, but CPU 3 gigahertz to 5. Damn. Well, let's see. So CPU speed, which is clock frequency, and RAM speed, which is data transfer rate, are different metrics. They don't directly correlate in a one-to-one way. Here's how they compare. CPU speed is measured in gigahertz and refers to how many cycles, or in cycles means how many arithmetic it can do in one cycle. So yeah, cycles is important. Cycles the processor can execute per second, and modern CPU typically operates between 3 gigahertz to 5 gigahertz or higher, depending on the model and workload. RAM speed is, measured in megahertz, which is and refers to the data transfer rate at of the memory. Like DDR4 RAMs typically ranges from 2133 megahertz to 4800 megahertz, whereas DDR5 can go up to 6400 or higher. The key point is that RAM speed doesn't need to match CPU speed. Well, I didn't ask for that. CPU's memory controller determines the maximum RAM speed it can support, but the actual RAM speed is set by the motherboard's BIOS setting, and the RAM's rated speed, for example, Intel, whatever this is, supports up to 266 megahertz natively, but with a Z490 motherboard, it can run 32 megahertz RAM via XMP profile. In practice, RAM speed is often higher than CPU's base supported speed, but the system will run at the lowest compatible speed between CPU and motherboard and RAM. This means your RAM can run at its rated speed at 32 megahertz, even if CPU only supports whatever speed it is, as long as the motherboard supports the higher speed. Interesting, interesting knowledge. Well, it should have been a common knowledge for all of us, but let's see. Now we are getting more basic, more towards hardware and all, kernel and all. Arithmetic requires, knowing how to cache efficiently, how to use contiguous memories, how to use CPU caching efficiently, how to vectorize data to use SIMD efficiently. Uh, what is clocking? What is overclocking? Overclocking is like going beyond what is measured and what is being told. I don't know. And what is blast kernel? Let's ask that. Uh, what do you think about blast kernel? What is blast kernel? Because if I ask this, it will go out of context and will start blabbering something. We might get stuck in something like theoretical loop that we are already stuck in because it is all new. WHATS. What's BLAS? Blast kernels or optimization. Hmm. So blast kernels are highly optimized low-level routine for performing fundamental linear algebra operations like matrix multiplication. Is GEMM. How is it GEMM? I don't understand. Like MM for multiplication, good. What is GE? Vector addition and dot products. These kernels are often written in assembly or using intrinsics to exploit specific hardware features such as SIMD instructions, cache hierarchies, and multi-core parallelism for maximum performance. Optimizations include blocking matrices into cache size tiles. So optimizations include like blocking matrices into cache sized tiles using microkernels for efficient computation. What is microkernel? And how does it even affect efficient computation? And leveraging architecture specific features like AVX. Well, we've heard about AVX over here in ChatGPT, but let's see what is this? But I don't want to follow up some links. So let's see. AVX or FMA. Libraries like OpenBLAS, Intel MKL, and VLIS implement these optimization, often achieving near peak hardware performance by carefully managing memory across and instructions scheduling, by managing memory access and instruction scheduling. Nice one. I want to know about AVX and FMA. External links? Yes, let's go. Ah, whatever this link is, CS Stanford EDU. This HTML is not very, responsive, which it should have been, but information over here is important, so go through that. So introduction. A common misconception is that BLAS implementation of matrix multiplication are orders of magnitude faster than naive implementation because they are very complex. This tutorial shows you internal intrinsics, FMA3 and AVX2. Now BLAS speed in dense matrix multiplication can be achieved using only 100 lines of C, and the code can be found here. All right, we'll go through that code, but what is that link? Uh, it takes us to a PDF. All right, we don't want to. It is based on a paper by Smith et al. Anatomy of High Performance. Oh, biological word in computer science. Anatomy of high performance many-threaded matrix multiplication. Hardware is CPU used in this tutorial. Also, it is some sort of tutorial, but let's see. The hardware, which is CPU used in this tutorial, provides 128 G flops peak performance, so 2 physical cores, 2 gigahertz, 32 flops per cycles, and then 2 physical core, which is 4 virtual I don't know what I'm getting into, but I think this is important. As well, micro architecture. 32 flops per cycle, which is 8 ports AVX2 and 2 FMA3 units into 2 flops per cycle per FMA, where flops is floating point operation and capital FLOPS is floating point operation per second. Good, good. Optimization and all that. Uh, Nave, then SIMD. Oh, oh. So impact of optimization on n into n matrix multiplication, whereas n is equal to 1920. Damn. So Nave is just 1.69 G flops, whereas SIMD is 13.39. Blocking is 51.75 G flops, which is G flops per second. Floating point multiplications per second. G is what? I don't know. Vectorization? Well, this is vectorization. Uh, and we are getting some C codes. I thought C was important, but not this important. Now threads are written. Can we write all these C codes in Rust? Well, we'll see that in future. As for threads and open blast, well, 120 and 102. These are some serious matrix. What is name? The name implementation uses three nested for loops. Various matrix sizes. So if we, get some n changed, so n to n various n, then it averages out to something like this. So open blast is this, and tutorial will give you something like near whatever this n is. So n was 1920, we are getting 121. Over here we were getting 120.25, which is near approximate, which is very precise, I would say. Uh, at 2880 we have decreased, so I think this was the biggest n or the largest G flops that we got from this sort of n. So 1920 is an important number. Conclusion is that even though Blast library is very complex to implement all necessary functions, right? So uh, is there any tutorial that codes can be found here? All right, good. So this was csstanford.edu, and we see some 11-year-old code. So yeah, readme is locking tutorial. This tutorial, well, I don't see any tutorial requirements. Open blast for comparison, disable if not interested. All right. Wikipedia pages instruction to compile run with this M experiments, name SAMD, various N, C, C++, and shell. Half, more than half is C++, better half is C, and then just some shells. Yeah, there's compile.sh. You're seeing matrix kernel. How many lines of code? Sorry, curious. So there's one or two. So less than uh, a bit more than 100 lines of code, and we are doing some real work. Full description is that PDF. I don't want PDF. We are directly writing registers back to C. Uh, 5 and then we are doing 5. What is this? Now, if you don't understand this code, well, it's understand. All right, I will go through this on my own time. For now, we go back to our whatever this. So it says now write Q4 benchmark function. No, before that, it also said something. Uh, says now return to question 2, which is strided memory. Why do strided arrays reduces SIMD efficiency in terms of CPU load instructions? Use SIMD load requires contiguous aligned memory blocks. Explain what goes wrong with stride 2. Let's get serious. Blocks. After that, CPU C, C caching, CPU caching. Very usable because of stride 2. So we cannot load large, you know, CPU caching becomes not very usable because of stride 2. VCTO C vectorization cannot be used because they are now not contiguous GUOUS in the memory, and we are not or being or allocated any memory. And this was 2, no? This is 2. Now 4. So what is 4? Write a full function. 10 runs, average time, separate averages, use per counter, do not benchmark list creation inside a loop. So let's understand what this code is. It says write benchmark and then dot. Let's copy this and maybe paste it just for the sake of instructions. These are some large instructions. All right. It says to write tab, then benchmark, benchmark, and we dot. Beside that, it tells us to, requirement is run 10 iterations. 10 iterations of what? Print average for Python and NumPy separately. So we want a dot product of Python and NumPy. So let's copy all those functions first of all. Where is it? Where is it? Where are you? These dot Python and dot NumPy. We'll definitely need these. Let's first of all go there. Like this. Let's define the these. Where is the import? You go above this. Yes, something like this. Give us some tab, tab, tab. Mm-mm. Doing it like this becomes not a very good option. So we'll not do it like this. We'll not even do it like this. We'll directly get the benchmark. Where is the benchmark? This is the benchmark. This is also called benchmark dot. All right. We'll get this benchmark. We'll get these also. But now, instead of simply just running this benchmark dot, RA, and then this dot, instead of calling it just one time, we'll run it 10 times and we'll store that in generic 10 times this benchmark dot. Will it work? I don't know. It should work, I guess so. But we should just write this benchmark 10 times and get whatever the average is. Now it says average time, use buff counter, print averages for Python and NumPy separately. So there are two problems. First of all, it doesn't return anything. So let's, you know, uh, port time, what time it takes. We are expecting something like return return rn return what? Return first of all. Okay. So that's what happens when you do something like this. And star. So it only exists in a Python sort of loop. Now we'll cut it. We'll say np time. Since it's not defined, we'll say np and time is equals to this. And over here also, we'll do the same damn thing. Py time. Doesn't know that yet. Py time, and we paste it. We have py time and np time. We'll return np time, comma py time. All right. Since we return these, instead of just doing this 10 times and printing it, since we are returning the value, let's silent this print statement. Silence this print statement. All right. Now both time. This is the first time I'm doing this, so let's go. This is both time. Now let's print that both time. So instead of just getting print, we print the both and time. So we get something like this. If we don't comment it out, we might see that exactly what we are getting. And what if we do it, 10 times, and we don't want these? They might print for 10 times, and we don't want. So this is NumPy, this is Python, and the same goes for, now since These are 10 times. We want to get numpy time. We'll do what? We'll run it using zip, and I think we'll get x and y separately. Will we get it? I don't know. Returns a tuple that is float and float. Yeah. Or we can just do, step size of 1 or 2. So 1, and it'll just skip this. We'll get 2, then skip that, and 3, and so on. But it needs iterating over it. So instead of doing multiply by 10, what we'll do is we'll run a for loop. Let's go over there. So for x comma y, how did we run zip? In zip, not this. X comma y. Zip. Let's see the example of zip, and then we can implement over here. So there was zip a and b. Where is this? Zip and b, and we used x and y separately. Nah, I don't think I should be using that. Let's just loop it normally, all right? And all the odd numbers, which are 1, 3, 5, 7, let's loop it normally. All the odd numbers are numpy, and all the even numbers are range 10, all right? We'll both benchmark this, good, but not like this. We'll say this doesn't look normal. Yeah, it does. It does. It somehow does. And it also makes sense. Because now we are getting this. And we're getting both time. What if we printed both time? Then the first or 0th index, not the whole 10th. Yeah. So if we can print 0th index, we can also print the first index. Copy this, paste it over here. 0, no 0, 1. Do that. We're getting Python and NumPy same at the same time. So now what do we want? We want to take the average. So we'll create a AVG for NP, which is equal to uh, sum NP sum, not sum, N NP sum divided by 10. Let's not do 10. Let's do C O U N T count. And I start doing 10 over here, because there should not be any magical numbers in a program. It will cause some errors and sometimes more problem than you might have thought. So count is count. What is NP sum? It is not declared just yet. So let's declare it. There is a NP sum that is equal to 0. And then what we are doing is NP uh, sum we are taking this both time and we are doing this. We're just taking the zeroth element and adding it. Then we are taking the average of NP. Good for us. We are dividing it by the count. Again, good for us. Now let's just copy this whole thing. Uh, Copy it over there, paste it, and instead of NP, let's do everywhere something like pi. All right. So over here we say it's pi. Over here we say it's pi. Over here we say it's pi. Again for this, pi sum, pi sum, pi sum, pi sum. Yeah, everything looks good. Looks good to me. Instead of printing these, which we can, let's just print more, which is print. Yeah, right. Nt print what? Avg numpy and avg pi. Let's do this. At the end, these are the damn it. It's e. All right, it's e. I thought yeah, it's very stupid of us. And I am seeing some discrepancies. Oh, these are not discrepancies, they are just e. Like, yeah, e. So let's do this. Copy it, paste it over here. Code is this, and we'll show it our output so that it can also calculate whether we did it right or wrong. Uh, Copy it. Let's paste it. Why are we doing this? I don't know. We're just doing this for the sake of doing it. Average pi is this, so that it becomes average numpy is this. What is this? Yes, no, it is something interesting. No, def. Don't use single one, just use double. Use double, not over here, over here. Now we run it. We should see some. Sorry. Sorry. Get it over here. Get it over here. Just undo this for a minute because we will be sending a new code. Average by average, whatever this is. We are defining it in nothing. We are defining it in nothing. So you can directly use it outside of the loop. It works. Should work. We're getting first of all loop and then average np average by less reading, less of everything. Nice, good for us. Now we copy this, paste it. I know it can be optimized, but I don't know how, and I don't want to spend much of a time optimizing some code that give us the same result. You will say output is this, and we paste our outputs and we press enter. Oh, there was so many things else also. Oh, nothing, nothing, nothing but Stride arrays in SIMD. Your answer direction partially correct, but not precise enough. You said vectorization cannot be used because of not contiguous. This is incomplete. What happened? What actually happens is SIMD loads instruction example. Conceptually is load 256-bit starting from memory address X. If floats are 8 bytes, then 256 is like 32 bytes, and CPU loads 4 doubles at once. For contiguous array, it looks something like this: x0, x1, x2, x3. Single aligned load work. Now for stride of 2, it becomes x0, x2, x4, x6, something like that. But you want something like this, and these are not contiguous. So that's what I said. Just I said this instead of explaining that it wants x2, x4, x6. But we have memory layout like x1, x0, x0, x1, x2, and so on. Now to compute SIMD multiply, CPU cannot load four needed elements with one instruction. So it must either load full contiguous block and shuffle extra instructions, or use gather instructions, which is slower. Uh, Use gather instructions, which is slower, or fall back to a scalar loop. Now this increases the instruction counts, cache misses, memory latency. If the issue is not vectorization impossible, it is vectorization becomes inefficient because data is not aligned. Also, we shouldn't have said impossible. We should have said it becomes inefficient because data is not aligned into SIMD friendly contiguous chunks, and precision matters. All right. Now the major issue is the benchmark is incorrect. Oh my god, my benchmark itself is incorrect. So your averaging logic is broken. Oh my shit. You're resetting some inside the loop. Oh shit. Damn it. Am I? Then damn it. Damn it. Yeah, I noticed. I noticed it too. I am so sorry. I was talking about optimizing it. It was non-optimized. It was even doing some negative work. Ah, so you reset NP sum to zero every iteration, so that's why average is so wrong. Ah, now it's right. All right. You divided value by zero. So now let's copy this and show it to a master or teacher. Let's go. Oh shit. Copy it, paste it. It pasted. Good. The numbers are realistic. Averages, whatever. So we see a code over here, which looks like this. It's look. It looks shorter also. By total and all that. Run 10 by size. We are starting and then starting from there. Oh, so instead of doing this and making it go 10 times, we are running loop in itself already. So pi total and np total, then we do this. I like this format because we are not copying and pasting much of our code, and we are not using. But since we already have this much of code, we could have just said return and just use this outside of whatever our code is. But let's go. Let's paste this. This looks nice. Module not found. Which module? Linear algebra. Yeah, there is no such module here. So we'll comment it out. We'll run it. It runs. We didn't call this function, which is benchmark dot. So let's call it over here. Benchmark dot. We're calling it. Let's see. Huh. it is very similar to, our average. Oh, not very similar. Yeah, it is very similar. It's 9.4 and it is 10. So very near. It is 5.9. This is 6.2. Very near. So if we run it again, you might see a different result. You see, now the average numpy becomes very similar. As for the Python, it is still 6, like 1/100th of a second greater. Now the numpy is becoming smaller and smaller. All right, so it says average, it is approximately this, Python is this, and that is 62 times faster. This matches architectural expectation. Now we move to deeper system reasoning before gradient descent. I don't know what that is. Question one, why memory bandwidth is often the bottleneck? You must answer this precisely like modern CPUs can perform. Yeah, see, we see something like G flops, and earlier, if we have seen something like G flops and all that, we would have sort of not understood anything. But after seeing this, blast tutorial or whatever this was, now we know there is flops, which is floating point operation with small PS. With big PS, it becomes something like floating point operation per second. With G, I think it is like giga flops. So gigabit of floating point operation per second. I think we have seen G flops also, G flops, but we don't know its meaning. There is like GEMM. So we don't need that. We need G flops, something that can explain what the G flop is. But we've seen that G flop is something that we measure in, optimization and all that. And one single flop is like floating point operation per second. So G means giga or something like thousands of thousand. Giga is thousand. I don't think so. Giga is over here. It says billions of floating operations. Yeah. So see, flops is floating operation per second, and we are doing it if billion times, then we get G flops. Very good. Very good. Now we can understand what this G is. G is probably for giga, and giga means billions. So good for us. Now memory bandwidth is limited to 30 to 60 Gbps on consumer system. That's not we saw. That's not what we saw. We saw something like, yeah, it was 3 to 4 GB. We saw something like 3,000, 4,000 in DDR5, 6,000 megahertz, which is not even acha. It is using small b. All right, small b. So no, it is using big B. So it is bytes, not bits. What is the problem over here? What we saw was megahertz, but this is gigabyte. So I think that might be the. But memory bandwidth is limited to 30 to 60 gigabytes per second on consumer system. Arithmetic is cheap, but moving data from RAM to CPU is expensive. Is it even asking me or just explaining it to me? So what is this? So you must answer this precisely like modern CPUs can perform hundreds of G flops per second. Well, yes, it can. And memory bandwidth is limited. What we saw over here was something like this. Impact of optimization on NN metrics. So without optimization, something like naive optimization, we get 1.69. And for blocking threading for open blast, we get the most G flops. Arithmetic is cheap, moving data RAM to CPU is expensive. Your algorithm is like reads large arrays, writes intermediate arrays, then memory movement dominates the compute time. Now, this is why it's slower than the temporary array doubles memory time. So it was not, I guess, answering me because it was not asking me, it was answering me. Let's read it more carefully because these are some important bottlenecks. Why memory bandwidth is often the bottleneck? You must answer this precisely. So, most CPU can perform hundreds, as we've seen 120 with open floor, whatever that was, open glass, open glass optimization. It can perform 120 G flops per second, which is 120 billion of floating operations per second. But memory bandwidth is limited to 30 to 60 Gbps on consumer systems, gigabytes per second, not bits because it's bigger B. Arithmetic is cheap, but moving data from RAM to CPU is expensive. If your algorithm reads large data arrays and write intermediate arrays, now then memory movement dominates the compute system. This is why this sum is slower than NP per dot. Why? Because this sum, what it does, it has told me, this ChatGPT told me something like it creates a temporary variable where it stores, a multiplied by b, and for that it makes loop. So first of all, it has to allocate for temp, it has to then clear it, it has to operate on temp. So memory movement is quite there. That's why it's slower than np dot. The extra temporary arrays doubles the memory traffic. Yeah, see the temporary array that we were talking about, it doubles the memory traffic. Now you answer something like, explain in your own words, why does high arithmetic capability does not guarantee high performance if memory bandwidth is limited? Be specific. I don't want to. Really, I don't want to. Why doesn't NumPy always copy strided arrays? So question 2 is, why doesn't NumPy always copy strided arrays? Well, then it has to perform allocations and all that. So its overhead also becomes something more than it should have been. Think about it. Memory cost. See, if it would have allocated memory, then it would have costed it to some memory cost, which is far slower than what a CPU can perform. Now, on copy, which is copying those numbers to create a more something like temporary array. Trade-off is there. If strided arrays are slower, why not automatically copy to contiguous memory? If strided arrays are slower, and why not automatically copy to contiguous memory? Well, to do that, we have to do some overhead operations, and that's costlier because memory cost is far greater than CPU, because memory can have a bottleneck which is at far lower range than what CPU can handle. So it might take more time to just handle memory, allocate it, use it to form a contiguous memory, and then use that contiguous memory to operate on. Phase 3 is gradient descent from search. Damn it. How many phases are there? Do not rush. Alright. I'm a bit enjoying it, but it's still a lot more to just grasp it one day. But it's better than to just, you know, stretch it over multiple days. So we'll do that. We'll answer this two questions. I'll try to answer it, but it will say something like, direction is correct, your direction is correct, but be more precise, or something like that. And I don't like that response. I'm taking a break for a few minutes, like drinking water and all that. So thank you. Oh, sorry, don't stop recording. Hello, hello, hello. So we are back. Runtime got disconnected, but we are back. And we were at question one. What was it? All right. We were at question one. So let's answer question one. Why memory bandwidth is often the bottleneck? Mm-hmm. memory band is often the bottleneck because of the speed consistency between the CPU and RAM, which is the first reason. Like CPUs have like 120 G FLOPS G flops with what? We saw something like open glass, no? 120 with open glass. Yeah. So with open BLAS, whereas RAM works at around the range of 3000 to 6000 megahertz. Right? So there's a cost difference, which is speed, and then so arithmetic is is much cheaper, cheaper than moving data around in the RAM of memory, which is first. Now, moving data from RAM to CPU is expensive. Arithmetic is cheap. Since SIMC, since arithmetic and operations are being uh, handled by CPU, CPU at much faster rates, RATES, much faster rates than compared to the data, the DHA that's coming from the memory, mem- memory. So CPU, so memory. So memory becomes the bottleneck in terms of need and data uh, transfer and all that. Let's move on to question number two. What is question number two? If your algorithm reads slash extra memory doubles the memory traffic. Yeah, let's add this line too directly. Just copy it, the space, just paste it. And now you answer why does high arithmetic capability does not guarantee high performance if memory bandwidth is limited. So high arithmetic capacity, just copy this, paste it over here after so is it high arithmetic capability not guarantee high performance if memory bandwidth is limited. All right, now question number two. Oh shit, I pressed enter. Damn it. Your question number one is conceptually correct. Now we define it RE. It always reminds me. But that's what we are here for. That's what learning is. So now we refine it to a system precision. What was the question two? Let's try answering it first. Uh, why doesn't NumPy always copy styled arrays? First of all, copy this. Uh, two, which is DEGAUS, because of the high arithmetic capability does not guarantee if memory bandwidth is limited. So COPYING, the data uh, creating a temporary what temporary array and all that, just so that we can give a con what is that, conjugated 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 what what's that word here? Shit, I always forget that word. What was that? Shit. Hmm. Conjugation. Flops capability. GBPS. What is that word? Keeping the keeping the element in array side by side, like all the indexes. Contiguous. Shit. I have to write this word somewhere because I always forget this. Contiguous. So that we can give contiguous array the arithmetic when it would be better to just give a strided element strided array for arithmetic than using more memory to speed up the process, which is already speedier, speedier than the memory, which might which it cause the memo, memory memory water neck. All right, this is the second answer. But before submitting this, we must read what it gave us for the response of our first answer. So this was the refined explanation. You correctly identified the CPU arithmetic through, throughput. What is this? Throughput is greater than RAM bandwidth. Arithmetic is cheap, memory movement is expensive. But let's express it in architectural terms. So modern CPU can perform multiple floating point operations, that is flops, isn't it? And in gigahertz, so gigaflops or G flops, GFPL, yeah, flops. As deep pipelines can execute fused multiply add, which is FMA, fused multiply add. But DRAM latency is 100 nanoseconds, DRAM bandwidth limited of tens to gigabit per second. CPU cache line is lagbhag 64 bytes. So see, it's 64 bytes, not just 240 bits or whatever that was. That was coming up to be 32 bits, 32 bytes. It's not 32 bytes, it's 64 bytes for now. If your algorithm requires streaming large data, cannot reuse data from cache, creates intermediate arrays, then performance is bound by byte moves per second. not flops per second. Now that is called memory bound workload. Dot product is often memory bound because each element is used once. Very little arithmetic per byte. Excellent, you understand this. And it will say me to answer question two properly, which is why doesn't NumPy automatically copy strided arrays? If contiguous arrays are faster, why not auto copy? Think carefully. Hints: copy is 0n, memory usage doubles, speedier than the memory. Have we added somewhere that copy will double the memory usage? Over here, which might double the memory usage. Yeah, and all that just so we can give a contiguous to arithmetic or the arithmetic, not mathematic, arithmetic, ARITHEMATIC, arithmetic, arithmetic, again mathematic, not mathematic. I want to say arithmetic, arithmetic, METIC, arithmetic, strided, stripe, strided, let's say. Then we'll move to gradient descent. I don't know what gradient descent is. So let's see. You're circling the idea, but reasoning is not yet precise. So let's clean it up properly. Why NumPy always does not automatically copy the strided arrays? Your answer mixed bandwidth reasoning incorrectly. The real reason are architectural and API design based. So copying ON, if NumPy auto copied every strided array, then before any operations, it would allocate new contiguous buffer, copy n elements. Now that is extra memory allocation. That's what I said, extra memory usage and all that for just speedier arithmetic. That's not needed. So that is extra memory allocation, that is extra memory traffic and extra latency. So if the operation is small and trivial, copy cost is far more than just compute benefits. So automatic copying could make performance worse. Now memory usage explosion. Imagine dataset is of 2 GB and several views created. Auto copying every view, well, you could suddenly allocate multiple extra gigabytes, and that breaks the scalability. NumPy is designed around views are cheap, copied are explicit. Copies are explicit, so they are not very cheap. Not all operations benefit from the contiguity, contiguity, contiguity. Well, not all operation benefits from contiguity. Some operations are reduction heavy or small enough or already memory bound. Copying would not meaningfully improve performance. So NumPy leaves control to the users. Like if you want to copy, you can. If you want to as contiguous arrays, you can. Now explicit control is critical for scientific computing. A zero copy philosophy. NumPy's design principle, which is slicing, returns a view whenever possible. Now, because zero copy data pipelines are essential in ML frameworks, signal processing, large tensor workflows, auto copying would violate this philosophy. Now you demonstrate SIMD reasoning, memory bandwidth reasoning, view versus copy reasoning. View is cheap, copy is far more expensive. Benchmark discipline. All right. Now it says that is enough. That we'll move forward, which is phase 3, which is gradient descent from scratch. And what is that? Well, we'll come to know about it. So gradient descent from scratch. Now we move from the performance theory, which is ML math. There is where the ML system begins. Step one is problem definition. We implement linear regression. We have seen this multiple times. Y is the prediction, W is parameter vectors, and X is matrix. But now we see something like D multiplied by 1, whereas matrix is N multiplied by D. What is D and what is N? Now we minimize this to sort of prediction becomes this. Hey, what is this? What is this? What is this? I think we transpose this y from over here to over here, so it becomes x over y, and w over y. But instead, what we did over here, all right, somehow we minimized this to this, which is 1 over n, and then summation of y predicted minus, or y prediction minus y total square, and then we'll sum it all up, and we'll multiply it, or actually divide it by n, multiply it over with 1 over n, which is actually dividing, and we get a MSE. Now what is this MSE? Now it says create experiment.py. Well, I just did somewhere, or did I not? Yeah, I did. uh, Task 1 is to write generate synthetic data set, and task 2 is prediction of future, and task 3 is MSE loss. What is MSE? And then fourth is gradient computation. Mathematically looks something like this, and we'll implement that programmatically something over here. We have x, we have y, we have w, exactly like this: x, y, and w. But what is t, what is n? Well, it is already defined somewhere else, isn't it? It is. It must be. Oh, I don't see. I don't see t. So where is the t? Where's the t coming from? Is t a constant? Because it is of different color. Where is this t coming from? Or is it a constant? It is what? We don't know. We don't know yet. Now your task. Implement everything, run it, print it, true weight, learn weight, final loss, training time. Answer these. Then answer these before we refine. Why do we multiply gradient by 2 over n? All right. What happens if learning rate is too large? Is this implementation memory bound or compute bound? Well, now ML is obviously what? Memory bound. Because we are moving multiple arrays to just calculate some arithmetic, which, can be done quickly. But since we cannot cache it and all that, we cannot take advantage of it. So we have to sort of transfer new data for arithmetic to perform. Till then, arithmetic gets done in microseconds, and then the CPU is sitting down there doing nothing, whereas memory is somehow trying to find the next computation or computational thing. That's what it's trying to do. So obviously this is memory bound, this question. Why? I tried explaining it, but as soon as I start writing it, it becomes messier. What happens if learning rate is too large? Well, it's good for us, isn't it? If learning rate, if no, 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 if learning rate, like the time it takes to learn something, is too large, then probably it isn't even learning anything. So it's a failure. But if learning rate means that it is learning quite quickly, which is too large, then I think it's good for us. But that's not what is asking. So why do we multiply gradient by 2 over n? We'll see that, or we'll try to understand it, because we don't even know what this t is. And why this 2 over n? It is trying to take delta of what? Where is this 2 coming from? So we had these for MSc, and what we did with it, I don't know. And what was this earlier, experiment.py? What was that? All right, we'll just create another, text first of all, and we'll say this is now experiment.py. We'll say experiment.py. Well, I see quite a lot of mosquitoes over here. Right, now we start coding. So task one is generate synthetic data set. So instead of breaking them down in multiple code blocks, oh shit, what did I just do? Ah, damn it. I just needed one line and copy this, paste it over here, go to home, try commenting it out. Our task one is this, and we will complete this task. How? We'll create first of all import, and we'll import numpy as np. That's what we always do. And then we say like define generate, and then data. Inside that we have n symbols, so we have n samples is equals to 100 000 000. Then we say something like n features n features is equals to 3. And spelling mistakes, I don't think so. Features samples looks great to me. Now we'll define this function by saying np.random not seed or seed. Now this is new for us. We have never used this, whatever this np.random.seed is, but we are now declaring it 42. Let's try bring it. It doesn't do anything because we have not, said anything about it. Generate. Oh, again, without doing any spelling mistakes, how can I even move forward? It's not possible. Generate data, generate, and data. And we are calling this function. I don't think I am seeing anything. So let's try printing it. Let's see what it does. Because I want to see what this actually does. We see none. Good for us. Yes, I think it is doing nothing, but that's not possible. So random number generation. So NP is numpy. Dot random is random number generation, which is this. Shit. Which is module random, and then use default RNG to create generator and call its method bit generator system that works with generator. Now these are some bit generator model streams, bit generators. Getting entropy to initialize a bit generator, seed sequence, legacy, random bytes, uh, permutation, shuffles, choices, rand n, ran f, random integer, random samples, randit, seed, beta, binomial, chi square, exponential, or chi square. Is It's English. You don't know. So exponential f, which is Fisher Decor distribution, gamma, geometric, Gumbel, oh, zipf. Oh, I see something that I know about. And then uniform. Good. Get state and all that. What is seed now? Random is generates random number, but what is seed? So seed is defined as seed, and it takes seed which is array like float, CO, it is none, it gives none. What is this? It is nothing that we should be interested in. So I don't know what it's doing, but we'll know. We'll know. We've seen random.rand n, so we know what that does, or we don't. We haven't read those descriptions, so we actually don't know. Welcome these boring things, but that's what they make interesting after something. So X, it's suggesting me X is something, but let's write it down by our own self, which is NP dot random dot random. Why that? Nobody knows. Well, for now, I don't know. Everybody or somebody could have known this. That's why it exists. It takes samples, not sample, and then comma. Then it has to be given n features, not feature. And spelling is mistake is NFEA. So features with A, not without A. There is no feature without A, but yeah. A typo R. Well, we are not defining Y right now, but it looks something like this only. Instead, it is different. All right. So after X, we'll say true, true, and then W. So true weight, or what? What is this? True weight. But it is not true weight. So we'll see true W is equals to np dot array, and after that we'll create an array which will look something like this. So 3.0, then we'll say 2.5, and sorry, it's 2.0, and then, and yeah, it was minus 2.0. So yeah, sorry, let's add a sign minus 2, and it looks well good enough. Give it a bit more space, give it a bit more space, and we need more space, so get a space. We say noise, noise, is equals to np dot random. Well, I have heard of some things like, seed and then noise and all that while making some sort of LLM or making them work somehow. I have, well, seen them somewhere or the other, but I didn't understand its meaning, and still I'm not able to understand its meaning. So it's clear that we will someday, but just not right now. Right now, we are just copying and pasting it so that we can know how it works, will it work. Oh, now there's attribute error. Why? Why can there be an attribute error? So noise looks something like this. If we comment it out, try printing it. So this is not the error. Comment out, try doing it. This was the error. So true w and np dot array, and then creating an array was somehow causing a error to occur. Did we do something wrong? No. Okay. So let's see what it does and what it says. Attribute error is like generate data, which is this function, and then we are saying that return char and char array. It says raises attribute error, has no attribute. Model random has module random has no R. and has no attribute. Oh shit, this was double shit. ARRAY. Yeah. So now it should be auto saving has been pending for 2 minutes. All right. Now what? Now we have noise, and then we'll create a Y, which will be first of all enter, and then we'll create a Y which is equal to X. Now we are seeing some suggestions. X, then at the rate, which is sort of multiplication in NumPy's language. Uh, we are multiplying by true W. Shit, what happened? It's rolling somehow. Hmm, it's not connecting. So it's true W. So true weight, true W. Then we are adding some noise to it. Noise. 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 So now we have noise and all that. And we'll return Y. No, we'll return X, Y, and true Y. RETURN. We'll return first of all X, then Y, then true W. There shouldn't be any errors. But we certainly did get all these things. Why? Who printed them? Nobody knows. If we don't do this, then we don't even get it. If we do this, we get this array, then this array, and then this array. Interesting. If I enlarge it, will it make some sort of sense or not? No, it doesn't. Let's try entering it again. Nah, it's not. It's not making any sense to me, at least. As for the true weight, it is same, which is NP array and this. X is NP random rand n samples and n features. What is n? N is 100,000, and n features, which is this n features. So it's taking that, it's creating np random rand n, which is I guess this. As for y, we are just multiplying with true weight and then plus noise. So where is the noise? Noise is this, which is np rand and n samples. So for all the 100,000, we are creating 100,000 samples, but we are minimizing it, or well, dividing it by 10, so to reduce sort of noise, I guess. So that's what we are getting over here, and it doesn't make sense if we magnify it or just keep it short, because this whole thing is nonsense as for now. Now what? Now we have returned it. Good for us. We have tried running it again. Good for us. But now we should. And let's just comment it out. Then we'll say define, or create a function called predict, which will take, first of all, define predict, which will take first of all capital X, then W, which is not true weight, which is only W. Now where are we getting this W from? Print 5 rows, test by printing 5 rows and all that. But I don't want to. How about that? I don't want to. Define predict, which will take this and will return return. Return what? Return X, and at the rate W. There's an error. You know what? Indentation. You know why? Because I did not add this colon, not semicolon, colon to it. Yeah, now good for us. Runs fine. We don't see anything because we did not, generate the data. But if we generate this data, we might able to, not GCC. Oh yeah, sorry. It's what I do in NeoBeam. So if we now generate or try generating the data, we are not seeing anything. I guess because of this. So let's keep it out. Now do this, and we are not generating. Mhm. Then we are defining MSE, which is MSE loss. So before that, task 2, just you know paste it over here and go to home, or just press this. It will automatically become a comment. Before doing task 3, which is, you should just copy this task 3, go over there, paste it, comment it out. Shit, it did not get, it did not got pasted. So ah, let's first of all copy it. Now try pasting it. Now comment it out. Yes, go over there, a little bit down. Now we'll define what? A function called MSE. Define MSE. And then use something like Y, and then PRED. We say something like Y and TRUE. TRUE. Y true and Y pred, which is Y prediction and Y true. It will return something like np.mean. numpy.mean. Inside that, we'll pass it something like Y and the prediction PRED, and we'll subtract with Y2. Then we'll multiply. Oh, no, we are raising an exponent to 2. So it's now to the y pred minus y2 to the power 2. So we are squaring it, which is something like this. Yeah. But, so many words. But we are not dividing it by 1 over n. Why is that? I guess it is because mean will do that. Mean will take how many predictions were there, and we'll just divide it by that n. I'm guessing that. So try running it. If there's no error, we shouldn't get any errors. I think it is smooth. Now task 4 is gradient computation. So we'll compute gradient now. What is gradient? Don't ask me. Shit. What the hell, yeah? What is wrong with this? I'm just trying to copy one thing like this. Paste it. Go to end. Now we'll implement a function called def, which is define and compute gradient. gradient. We'll compute gradient. We'll pass capital X, we'll pass Y, and we'll pass W. And then colon and come down, we'll say N, which is equal to X dot shape, which is then 0. Then we'll return what? return 1 over n, 1 over n. I don't know why we got 2 over n all of a sudden, but before that we did not. 2 over n, we with multiply it with what? X t at the rate, like that. Let's do x uh, at the rate w minus y. Seems good, looks good. Now we have a task 5, which is this gradient descent loop. Now we created something like compute gradient. Now we'll create something like train, which is gradient descent loop. We don't know what it is computationally, and rather, theoretically, we don't know what it is. We'll go over there and say define what? Define train. It will take x, it will take y, and it will take IR, LR, LR, which is equal to, let's give it a space, 0.01. Then EPOCH, epochs, EPOCHS, epochs is equal to 1000, not 10,000. All right. Then you go here, we say W is equals to MP dot zeros, ZEROS, so zeros. And we say something like X dot shape inside that, not shape, just shape. Then we'll say 1, it will shape 1. What's next? We'll say for I in range of what? Range of epochs. So if I is in range of epochs, which means 1000 times, we should do what? We should do gradient is equals to compute. So we are computing gradient for 1000 times using x and y and w, and doing what then? Then we say w minus equals to, so whatever w is, minus that, and then assign that LR multiplied minus LR multiplied by gradient, and then assign it that value back. Shit. Well, it's definitely a maths, but we don't know what it is being used for. I is, if divisible by 100, it means, I mod 100 equals to 0, which means you are dividing I by 100, and if the remainder is 0, then what? Then we should do something like loss is equals to MSE. Then we'll say predict inside that, and we'll try to predict what? Predict was a function. So inside MSE, we are passing predict, which will give us y pred or y predict. But for predict, it needs x and w, capital X. All right. And then y pred is passed. So y pred is like y prediction. We've seen y pred somewhere. What somewhere? We have seen it over here. Here's the y pred. Yeah, y prediction and y true. And prediction is like this: predict x and w. So we are passing x and w to MSC, which is y predict and c. This is y predict and y true, which is just y. Y true is just y, right? So I think it somehow doesn't make sense, but it is starting to make sense, which because we are using it somehow, which is this. Mhm. And this is the loss. So loss is equals to MSE, and whatever the value of MSE is, MSE is returning what? MSE is returning this mean of y prediction minus y true and to the power 2. That's what the loss is. And if we say now print, and then we say F, which is format what? Epoch, cite that I, and then what? You say loss is loss, and then what? Nothing. After printing it, we at the end of the for loop, we say return W. Return whatever the W is. So using this train, we return W, and there is no error after running this, but we don't even understand what is happening right here. So now your task is to implement everything, run it, print the true weight, learn weights, final loss, training time. When I've heard of them at the first time, so uh, I have I have heard its name for the first time. So please explain before asking questions like what is going on. And here is the written code you pro you provided. As per y is there e, should be like this, WRITEN, WRITTEN होता है ना, EN, written. And going on is separate. What is separate. I heard THIS, not this. It's this. At the end, just use this, get a new line, paste it all, then get a new line, then copy all these code, copy it, paste it on the new line, and we'll say, let's go. Good, you did the right thing. You stopped and asked for the explanation before blindly running the math. Now we teach this properly from first principle, no skipping. What are we actually doing? We are solving this problem. So given the input, which is X, which is matrix of size n into D, target, which is Y, which is vector of size n, and now we want to find W, which comes under RD. What is this RD? Such that XW is now similar to Y. This is linear regression. I still didn't understand it. So please, instead of going, first principle, go first, beginner human level. What does this generate data do? X numpy dot random dot rand n sample and n features. So this creates a matrix of x11, x22, and all that. All right, each row is equals to one training example. Each column is equals to one feature. Then we say, oh, we are not actually running, training examples. We are just giving it some random data for now, and we are just making maths work. And for features, we are just giving it again some random data, which is n feature and n sample. Can we see that? Where is the n feature? N feature, where is the n feature? Shit. And random, n sample and n feature. Where did this come from? So it already has an n sample of, oh, so we gave it a n sample of 1000. So it will go for, 1000 columns. As for the row, we are seeing 3 rows, which are n features. But it says each row is one training example. So of these 1000 or 100,000 samples, we create each row, which is like this, one training example. So each row has 3 features. So one, two, three, yeah, 3 columns, and 100,000 rows. So yeah, it's mathing right now. Maths is mathing right. So we are seeing something like there are hundred and thousands of, so it's like this matrix is of size 100,000 multiplied by 3, which is, well, magnanimous or magnanimous, well, huge. Magnanimous is like Dilwala types. Huge or, well, enormous, giant size. Now each column is one feature, each row is one training example. Then we say something like true W, which is this. It is true W. NP array. What is this? This is the real relationship between input and output. So mathematically, this y is equals to 3x1, 2x2, and 1.5x3 plus noise. What does that mean? Well, nobody knows. For now, we are trying to understand it. So these are, the values a, b, and c. 3, 2, -2, and 1.5. ax1, bx2, cx3, and plus noise. So a is 3, b is -2, c is 1.5. This is the real relationship between inputs and output. How? Nobody knows. So mathematically, this. Then we are seeing something like y is equals to x multiplied by true w plus noise, which means this noise is over here. And since we are multiplying x and true w, it means it should make something like this. Whereas true w is this, and x is the equation of x1, x2, and x3. So if we multiply noise, which is true, sorry, if we multiply true w with x, we should somehow get this. So the data set is synthetic but realistic, and we know the correct answer. The job of training is recover true w. So whatever this true w is, just recover it from the whatever the equation gets to be. Now, what is prediction x and w? So it returns x at the rate or multiplied with w. This computes y is equals to xw, or the y cap, which is vectorized form. So y cap is equals to xw. So this is vectorized matrix multiplication. What is MSE? Well, it is mean of y bred minus y true to the power 2. So it looks something like this. This is MSE. Y square penalizes the large error more. So if there are more errors, it penalizes it more. Or there are large errors, then it penalizes it more. And y square, because it's differentiable. You can differentiate. Why do we want to differentiate it? Now this is our objective function. All right. What is gradient? We want a minimal MSE. To do that, we compute it by delta MSE by delta W. This tells us what? In which direction should we move W to reduce errors? After doing the calculus, you don't need to derive yet, but it is something like this, which is 2 by n x to the power t x w and y. What is t? Nobody explaining it. So that is what this line computes, which is this. So where is this line? Where did it go? It is here. So it computes the gradient. So this is our gradient. Now step 5. Oh, Yeah, there is a parse error, which is KATEX parse error. Expected EOF and got this at position 24. What if we try to copy it? You know, in a text format, if we try to format it. Ah, not a code. Shit. Not a code, not a code, not a code. A text. I don't see a text. What does it make? Ah, it's different. So we know what is this? This is gradient or gradient shift. What is it? Yeah, this is gradient and gradient. Where is this? This is compute gradient. So we are computing the gradient. And now the step 5, which is generate gradient descent loop. So gradient descent. What is gradient descent? So gradient tells us the slope direction. So we update W is equals to W minus learning rate and times gradient. Now this moves parameter downhills. Repeated 1,000 times, it should converge. Now before running, you must understand conceptually what is the shape of X. Nay, what is this shape of? So, what is the shape of X? What is the shape of W? What is the shape of? So let me try and recall it from here. So X is what? X is a matrix of 100,000 rows. We'll write like this. X is a matrix of 100,000 rows, rows, and three columns as given in the program. All right. Now, what is W? W is matrix of, because we want to understand the shape of it. So, shape of what? Shape of matrix, I guess. So that's what I'm telling it. That W is matrix of one row but three columns. One row, three columns, three columns. And now it asks that what is this? So if you multiply, 100,000 with three, with one row and three, so it converges and it gives you 100,000 with three. So it's like this. If you do this math, which is like matrix, and you do this, multiplication of this whole damn thing with another matrix which is of size 1 into 3. So what happens right now, well, I remembered using pattern. So it was not X, it was 3, right? It was 3. So what happens is the first element of first row along with this column vanishes and it gives you a matrix of this size. So we'll write X at the rate W is matrix of size this 1,000 rows and these many columns. Now what about xt? I didn't understand what the t is. Xt, I didn't actually got what the t is. Therefore, Ting. All right. Given the sample is this, write exact dimensions. So I've exactly written the dimensions. W is a matrix of this. W looks something like this. Uh, one row, three columns. These standing ones are columns, so they'll create three columns. It's like the building has a column and it is standing, so that's why we see this standing. And rows, well, we know we sit in rows, so yeah. Why do we initialize W with zeros? Well, we did not. We initialize it with true W, which is 3, 2, and I'll just write this exact thing. We did not. Now 3. What is 3? In x, t, and whatever we are doing over here, why does x multiplied with y minus y represent conceptually? Well, it should represent gradient. Gradient or what? This is prediction, and when we use prediction minus y times u, then we get MSE. But if we do this, what is this? What does this represent conceptually? Compute gradient. What is this? This is prediction minus y, which is the truth. So I think it gives us how much of the, if x multiplied by w gets correct, which is prediction, is if, near to y, then if the value gets near to, if this value gets near to 0, which means that we are near the true value of y. That's why if we are multiplying this x with w and minusing y, we are getting near 0. If it is far from 0, it means x at the rate w is far from 0, then it means we are doing something wrong. We are generating some sort of error. So I think what this represents is gradient, and I know the explanation, so I will just try to write it down. I think option B, which is error, not gradient. Sorry if I ever said that, because I think I did, but it's vector. Error vector. VECTOR. Conceptually, if we think about it, the x at the rate w is prediction, which is trying to get the true value of y by predicting it. All right. So if this value value which I see as which is this is near 0, we are able to or are close to PREDICTIMG term 1. If not, then very far from from the ACTUAL to Y. Now I did explain. Let's go. Good, you are reasoning. Now we correct precisely. Yeah, I need correction right now. There are dimensional mistakes and one conceptual gap. So shape you made error with. Since n is 10,000 and features is 3, so you said 10,000 rows and 3 columns, correct? Shape is this. Yeah, exactly. W, you said 1 row, three columns. Well, that's what I saw here, but it says no. Oh, I think 2W and W is different. So here it is 2W, which is this. All right. And what is W? Where is this W? Ah, this is the W. So, shit. X dot shape 1, I don't know what it does, but, and we are initializing W with zeros. Now we know we are initializing W with zero, not not 3 and minus 2 and minus 5. This is 2W, and this is where we are initializing W with. Damn it. So let's see. So W is this. So W is a 1D array. Yeah, shape is like this. So it has three rows, like row wise row, 1, 2, and 3, like sleeping rows, like 1, 2, 3. As for columns, well, don't know. So important distinction. W is a 1D array. This, you said this gives us this. Well, I expected this W to be, of size 1 comma 3. But if this is not, this is only 3, then we get a 10,000 with nothing. Something like this. Yeah, 10,000. Sorry, 100,000 with nothing. Now, all right. I'm going to take a break because this was a major breakthrough in concepts, and I think I will need a break. Don't deserve it, but need it. All right. So we are so back right now. So we left it over here. So X multiplied by W, which is, well, since W is of size, this is the matrix of W. Then if we, using our old formula, old funda, if we take the x which was 100, let's use this, which was 100,000 and multiplied by 3, and the a which the y was, not was, now is x, now y is something like, looks something like 3, and then we don't know 3 comma, and we don't know, so let's keep it underscore. So now what will happen is, uh, the column of this and the row for this will get deleted, and what we'll get is the real size of a new matrix. This is a x at the rate w, and that is exactly what we get. So our fundamental is clear. It was just, we were not clear about what is w and what is true w. So true w is this over here, this true w, whereas w is this, which is first of all zeros, and now it's taking a x dot shape 1. What that does, I don't know, but it is zeros. It is filled with zeros. So I think we got asked that why it initialized with zeros. Yeah. So now we know the size of x multiplied by w, which is this, and it is a vector of prediction 1 per sample. All right. Now you said you don't know. Good, we'll fix it. T means transpose, and transpose swaps rows and columns. So if there is 100,000 rows and 3 columns, we'll get, yes. In matrix, if you wrote something like capital T at top of the matrix, well, you get a you get a transpose of it. And now the transpose looks something like, the rows are now 3 and columns are, well, 100,000. Why do we need it? Because gradient formula requires it. We require the transpose of x. So good. Now we know xw, sorry, we know the transpose of x, we know x and multiplied by w, we know the y, which we are trying to minus. So yeah, and when we try to multiply these, then we get a matrix of size 3 columns, 3 rows, and we don't know how many columns. That's what we get. That's what it's telling us, that we get a matrix of 3 and 3 rows, and whoever knows these columns, maybe. So which matches the shape of w? Yeah, exactly, which matches the shape of w. So this matches the w. So we are trying to get gradient formula. What is gradient formula? This is gradient formula. Why are we doing this? Where is it? Gradient, where is it? Compute gradient, isn't it? So this is gradient. So I guess w is now gradient. Is w the gradient now? I don't know. So everything dimensionally aligns. Now this is linear algebra discipline. Well, I think I'll have to go through linear algebra again. Now initialization, well, I was wrong. Sorry. There's a distinction between 2w and w. That's what I learned even after writing this code. Sorry, I am very sorry. I'm truly sorry. Now you said we did not, we did not. Shit. What I said was embarrassing, but let's correct it. Correct observation, but true W is ground truth used to generate data. We do not use it during training. We initialize W with NP zeros. Why zeros? Because linear regression loss is convex, which means at starting point converges with proper LR. We are seeing proper LRs into grad. Alright, 0 is simplistic and deterministic. Random would also work. So yes, random works too. Now what is x multiplied with w and y? I think this is w. Error vector, well, this is gradient. Now I know this is gradient. Why do I know that? Because I can see it somewhere. This is predict. This is gradient. I think so. Let's see. So correct. More precisely, x w minus y, which is a vector residual. So each element like yi and yi vector minus yi. Now it is near zero, then prediction is good. So gradient is built from residual. It is gradient. Excellent reasoning, but wrong answer. All right. Now deeper conceptual check. Before you run training, question one. Why do we multiply gradient by 2 by n? Well, that's what we got. What happens when differentiating the square? Ah, shit. Yeah, yeah. When we differentiate with square or 2 in integration, we add the power. In differentiation, we minus it. So we get the 2 over here and we minus the 2. So error becomes 1. Now we have 2 by n and the error. 1. Yeah. In differentiation, we multiply by exponent and minus 1 from the exponent. That's what we do. So that's how we got the 2, not another 2. That's it. Now question 2. If learning rate is too large, what happens to loss curve? Be specific. It converges or slowly oscillates, diverge, and why? Well, did I get the answer for this? Somewhere? Nah, I did not. So if learning rate is too large, what happens to the loss curve? When learning rate means you are learning quite greatly, then loss curves is like calculating the loss. So if loss is high, it's going high. If loss is minimum, it comes down. So loss curve diverges or converges. Earlier, let's say this is x, this is y. We are seeing loss curve which was very high because loss was initially very high, and then it starts to learn too quickly, so it starts to come down. And let's see the same thing which is learning, which was too low, and then it starts to go towards as soon as loss comes down. So they both uh, convert slowly, isn't it? And after converging, after this point reaches where the learning surpasses the loss curves, then it starts to diverge. So let's do it. So let's do, if initially loss was too high and the learning was shit was too low, then the graphs were distinctly distinctly far from each other. But as soon as the learning rate rises and losses comes down, we get a point where where they converge, and then after that point we shall get a divergent curve where learning sur- surpasses the losses rate. I think this is it. I don't need to specify further because I don't know further. That's my moonshot or the long shot that I didn't expect to know something like that. Now, question three is system level. Each epoch computes. So, what is epoch now? Each epoch, let's say something is epoch, let's say something is epoch. It computes something like this thing, and then sort of gradient. Now, this touches full data sets. Given these many matrix, is this compute heavy or memory heavy? Uh, it's a obviously memory heavy, HEAVY, because compute is just for may well no. Since matrices are very high, I think this is compute heavy. Oh well, of course. OFQRSE. Of course, uh, still, of course, it is compute heavy because of such large matrices. MA, not AM. Matrices calcu calculation. This is not compute heavy. Let me think of reasons. First of all, we are calculating metrics, and calculation of metrics does not, run parallelly. Like you can just calculate everything at one time using caching and all that. You need elements of different places from all over the list or matrices. So it is not, of course. I don't know. You need to calculate matrices, which means element of element from FR from different places in the matrix and in the matrix, different places in the matrix, which compute wise is not that heavy, but moving and reading, reading the data makes it mem- me- memory bound. So here I think memory is the bottleneck because compute wise is arithmetic, which is simple compared to sending data from the matrix to be computed. Let's go. Good. You're thinking. Well, I always think. Now we refine and correct precisely. You said differentiate exponent and multiply by 2, correct direction, incomplete reasoning. Well, I use some short words. Yeah, obviously. Let's derive cleanly. So we have NSE over this derivative of error, which is x w minus y. It is the error. Now we do is what we do is 2, which comes up over here, and we then minus 1 from the exponent. So 2 minus 1 becomes 1, which is like nothing to the power, and 2 comes up to the multiply. So gradient becomes something like this: 1 over n multiplied by 2 multiplied by x transpose and then error. So it becomes something like 2 by n. The important insight is 2 comes from the derivative of the square. Yeah, obviously. And 1 by n is preserved because of its constant scaling. Correct. So it was correct. It's just, giving us some good visuals over here. I'm guessing so. Now, learning rate behavior. So your answer is confused. Let's clean it up. If learning rate is too small, converges very slowly. If learning rate is too small, converges very slowly. If learning rate is moderate, converges smoothly. If learning rate is too large, updates overshoot the minimum. Loss oscillates, can diverge. Loss increases exponentially. So the correct behavior for too large is oscillation or divergence. So both. Not learning surpasses loss rate and all that. So precise mental model, shit. It didn't even acknowledge my answer. Oh, that hurts. Well, all right. We are here for the game of being hurt. A precise mental model is gradient descent assumes local linear approximation. Large step avoids that approximation. And now question 3, which is memory versus compute bound. You said arithmetic simple, moving data makes memory bottleneck. Correct. Now let's quantify how much. So, all right. Answer is correct, which is not that compute heavy but memory bound. Why? Because we have a matrices of 10,000 rows and only 3 columns, but 10,000 rows, that's important. And each epoch, which is like x multiplied by w, reads entire x multiply 300k numbers, which is 300,000 numbers, and then we get a transpose of that x. It read entire x again. Now, arithmetic per element is very small, like 1 multiply, 1 add. Data movement, whereas, is like 2.4 MB per pass. So it's like 1000K multiplied by 3 multiplied by 8 bytes, which makes only 2.4 MB, but it's per pass. So it's not the whole calculation over here. 2 passes per epoch, it's approximately 1000 epochs. So multiply multiple GB shit. It's like 2.4 GB per pass. So yes, this is memory bound. Excellent connection to previous theory. Now we run the training. All right, let's see. So add this at the bottom. We will. And what is this? We have x, which we have y, we have true w, and we say that generate data. And since generate data returns something like this, where is this? Where is this? Where is this? Is this generate data? Yeah, over here. So it returns x, y, and true w. So we directly get the value, and then we say something like start, which is a time of counter and whatever, and we do our business. Don't do this to me. Don't do this to me. All right. Now we get we should add oh damn it. We should add a new block, but I am not adding it so that it remains very uniform, that we are doing it all together. It's not segregated, because segregated means making no sense at all. Now we have this from generate data, which is a function over here. Generate data. I want to see Python. Then we say start. Then we do something like learn w is equals to train. Now train is this, which is gradient descent loop. This is now train. This is an epochs of 1000, like 2.4 GB should be now memory bound. So we should see something like RAM getting rammed up. For now, it is 1.8 GB right now, and this is normal. So we shall see how it runs. Now run it, and expected behavior is something like, see, if I try to run this on my computer, this is 70% like CPU, and out of which the 50% is consumed or getting consumed by my OBS app, which is this recording app. So, well, that's why I chose this savior of mine, Google Colab. Press enter. Damn, we didn't even got the time to enjoy this best. This was like so quick. What happened? So we directly send eggs and epochs of 1000. We say Ella and whatever. We get true weight, learn weights, training time, which is n minus star. Then final loss, which is MSE, predict, and whatever this is. All right. We didn't see much of fluctuation over here. Ah, let's run it again. Some dramatic effect should happen. Nothing, nothing. Let's see. Run it continuously. I am not seeing at all, like not even single percent of RAM is getting expended right now. So I think it would have been safe to just run on my computer. But all right, since we are doing it on collab, we are still all right. So now learn weight is something like this, which is near 3. Now this is near minus 2, and this is near minus 1.5, which is good, which is actually good, because this is our true weight and this is our learned weight from prediction from predicting it. And I think this somehow is good. And we only see epoch 900. Why? Why? Well, I wanted to see epoch for whole 1000. So let's just copy it first of all. Copy it and paste this data. And now let's do something magical, which is sending more epochs, something like add 2 zeros or 3 zeros, let's say, and see if this gets even somewhere closer to our actual data, or well, surpasses it. And now we see some RAM. Well, we should see some RAM getting rammed up, but still nothing. Well, what the hell? Mhm. I see no fluctuation in RAM. I think that is stuck. That is stuck right now because RAM is getting rammed up. That that's what we know for sure. That's what we know for sure. So epoch is approx 100,000. So is near it. What is 100,000 or 1 million? So we are not seeing anything from our RAM. So let's close it. We don't want to see this data also. Let's close it or move up. And well, it was a million. Sorry for me, but I want to see what happens. It's not even a near million. So, well, it will take time. So let's spend some time over here, right? And let's enjoy this. Let's enjoy this code happening. Let's see if it even gets something near like 3. I want to see something like 3 and minus 2 and 1.5. If that happens, it's amazing. It's magical. And somehow, raising this epoch value can make your training work. Ah, it is now near a half a million, not dollars, but yeah, half a million. whatever this number is. So 50K, sorry, 500K, which is half a million. Uh, get to the half million, get to the half million. We have spent 2 minutes. We can see over here, we are executing 2 minutes and 4 seconds. RAM is still not ramming up. I don't know what's happening over here, but if that has been my computer, well, I would just, it would just crash. What I really need right now is Mac Studio or something like that, because it has MLX and it uses system RAM as GPU's RAM, so it works best or something like near good for AI right now. Right now, what's there in market, MLX runs best. Plus, it's Apple, so we know that it doesn't require much of maintenance for sure. When will I get a better computer so that I can stop relying on this? Hmm. Or else I could just rent out some, Amazon, some VPS machines. Well, that's private machine, but you can do whatever you want to do. You can make it public. You can, crash that whole server down. You can do whatever you want to. Well, I've never used a VPS machine, but if I do someday, I will first of all, my first command would be sudo rmrf and no preserve. So just wipe out the whole memory. Then you'll see uh, after how many hours we get a revive of our computer, whatever it is. So we ran it, and expected behavior is loss decreases steadily. Well, it seems so because it was 0.2, then it became 0.01, and then near it. And loss is persistent over here. So we see no improvement, just the training time improved. So final loss, which is this, is somehow comparable to this. So I think the million epoch didn't work out well for us. So I think the longer you train your data, the more spending your time. How about in just 100 epochs? Well, now the accuracy is bit more less. Loss is nearly 14. Training time, well, decreased a lot. Well, it decreased a lot. So how about just 700? What's our lucky number right now? Ah, now we don't care. Now it comes that we don't care, because this seems like this, whereas this ran for how many, 700, as this ran for 1,000, and the earlier one ran at a million times. So now we know running a model a million times doesn't make much of a change. But we should appreciate how close the value they are actually. Oh, it's good. It's nice. And I think every time they will be a bit different, or they are not. Well, for now, they are not. And we are running it for 700 times. We are only seeing for 600. I don't know what's happening. Is there any error while printing or print mistake or something like that? Huh. So changing the epochs can sometimes reduces. How about we say 900? 73118. 73118. So it doesn't change until and unless we make it 910. Then it might. Yeah, it did change by just a little. So if we say 900, it will revert back. It didn't. It didn't revert back. Good for us. 100? No, we need 1000. Shit, what's happening? Run it, leave it. You're good to go. So now what? It says excellent. This is now correct convergence behavior. Let's analyze it like an ML engineer, machine learning engineer, not a script runner, a ML engineer. So convergence analysis. So initial loss was something like 14.57. Now the final loss was near, 0.01003, exact same. So it's 14. Yeah. So it is a hundred 1400 times reduction. It's like 1450 times reduced errors. So loss stabilizes around epoch of 400. Over here it stabilizes to this value, but goes on for these values, over here. Yeah, over here. These changes. But that also stabilizes over here, 1 5, and then it becomes 1 5. We see all the 1 5 1 5 1 5. So then it becomes safer for this, which is 5, and then it becomes 2 2 2 2 2. Now it's safer for this because after 6 it becomes 5 5 5 5 5, and for 7 it becomes 7 7 7, and for 8, well, this is eliminated. Now this is 7 7, and this is 2 2, and this is 6 5. It means this one somehow. Let's run it a bit more. Add two more zeros and run it. Now let's look at the convergence error. Same. So for when it became sort of this same, just copy this number. Let's realistically, first of all, just how to interrupt this here. I want to interrupt this. Interrupt it. Well, it stabilized somewhere. This number stabilized somewhere around what? 893, around 1600 rounds. After that, it became sort of same. So let's run it for, just 1600, exactly 1600. And I think we are the closest that we can get to our data. And this runs even faster. So 892, 893, 892. All right. And we get near close. And now the final loss is less, or more or less the same. Now that means learning rate is 0.01 is appropriate. Our system is numerically stable, optimization is smooth, which is convex problem. Learned weight is true, and learned is like this. Difference is tiny, which is approx 1 e to the power minus 4, which is base 10 to the power minus 4. All right. Now this is correct. 1 2 3 4. Yeah, base 10 to the power minus 4. Now this is correct given the noise in the data. Your implement, oh, there's also noise in the data, so it can never be, actual correct. Like it can never become the 3. Oh, thank you for telling me that. Now your implementation is mathematically correct. What about I run it for 1700 times? What now? Do I see some stabilization? It's stabilized at 1400, destabilized at 1500. So it sort of oscillates now. It sort of oscillates back and forth. The implementation is mathematically correct. Now, training time is 0.22 seconds. For these many samples, 1000 epochs, full batch gradient descent that confirms efficient vectorized implementation. No Python loops inside training, which is good, very good. Now we stress test understanding. You must now know two experiments. So experiment A, which is large learning rate. So now we stress test understanding. You must now run two experiments. So this is experiment A, which is we have to set LR to 0.5. I don't know what that is. We'll know that. And run 200 epochs. Observe the loss. Answer, does it oscillate, explode, or still converge? And explain why gradient. Experiment number B, very small learning rate. Set LR to, very small learning rate. So I guess LR is the learning rate. All right. So if we set it to very small, or if we set it to very large, what is it right now? What is the LR rate right now? So LR is LR. What? Where is the LR? Where is the LR? LR is 0.01. All right. So it's very low compared to 0.5. So we increase first of all LR rate, and then we'll try to decrease that LR rate. Good for us. And explain why convergence slow and all that. So what I'll do first of all is just copy this whole thing, create a text, fail to copy to Clue. Oh, copy it again. It copied. It got copied. So let's paste it over here. First, now what? After you answer, remove this, remove all the questions. I want to see questions, conceptual deep question. Nah, yeah, these questions. Yes, because we are performing experiment. Experiment A, experiment B. Yes. Before that, no. We don't want to see these. 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 Let's analyze. Analyze quickly. Let's analyze and analyze quickly. Ah, let's cut it. Let's create another text module, paste it, and now we have experiment A, experiment B. Now what do? We, sort of replicate the whole experiment by copying this cell. Uh, hmm. Now we paste the whole cell, and over here we code and we paste the whole cell. Now first we'll run what? We'll run experiment A. So experiment A is something like this. But before that, we don't want to see the output. So LR becomes 0.5. LR becomes 0.5. Where is the LR? It is here. So it becomes 0.5. Over here, we'll say of this, we'll say something like LR VECOMES 0.5. Oh shit, becomes 0.5. LRBCOMES. Seems right. Seems right. LR becomes 0.5. We run this. Now let's see. Still there. It's still there. 893 in, well, 1600. So I don't see much of a difference. Well, there certainly is some difference, but not much, because what I actually see that I can't actually see it. It stabilizes around 400 again. Trading time just increased because of these 1600 epochs. As for LR of these, let's copy these value because I could miss some zeros, and let's go over there and paste. First of all, yeah, now paste it. All right, after doing that, let's see what the difference it makes. So it certainly doesn't make much of a difference. That's what I see. It didn't make much of a difference because 73122 over there, this is 17. Ah, 73122. All right, 73122. 731. It's exactly the same after 1600 epochs. Even these rates are same. So I don't know if it expected something great or what. So if we change from 1700 to just 1000 so that we can see that it is a real data. Yeah. Now let's do that also for 1000. And now let's compare it. All right. We'll do that for 1000. Now let's compare it. We see something like 73121. We see something like 73121. I don't see much of a data. I don't see much of, well, I can't see much of the data difference here. It looks the same to me after changing the values. First this, and then these. LR is 0. Shit. I pressed shit. Let's stop it. Let's stop it. Can we? Can we? Nah. Try. Let's try something it somehow. Good catch. If you're seeing identical results after changing learning rate, something is wrong in your experiment. I can already see the issue. What is it? Not this issue here. This is typo. You can't understand this is a typo. What sort of AI are you? That suggests the learning rate may not actually be changing in your train call. Let's debug it. So this is a train call. Over here, we have already defined Ella by default. Oh shit. You should have changed this. Oh damn it. 0.5. Ah, all right. Since this is 0.5, you know, now let's change this. Where this? Where is this? Yeah, something to worry about. We should have been worried, but we were not. Why weren't we? This is such a big mistake. How can someone make it when I did? I just made this error. This is called human error, and AI can catch it. So it didn't got my typo error, but it did. So this is 73122. Let's go over there. It is well very different, obviously. Yeah, shit. My CPU is like blasting right now, so I don't think I can work out with this. I can't even think about like learning Rust right now because this is too much. And time I took is nearly like it's 10 o'clock. Well, 11, nearly. Not. Yeah, yeah. We get different data. Yes, it was a human error. All right, let's press enter. Let's copy it and paste it. We don't need to mention LR because we can clearly see which value is which because of the loss and learned weight and all that. This is not even somehow near 3, whereas this is very near 3. So learning rate over here is very terrifying. It's not even near 1. What the hell is going on? Excellent. Now we analyze properly. You have two very different behaviors. Good. Case 1, LR is 0.5. As we sent it, this was first, that was second. So loss is very small decrease of loss because it's nearly 15. Well, it should be closer to 0 so that we will say that loss is now reducing, but it is not. It is not. And weight code is, well, not even near 3. So this is interesting. It did not explode. It barely moved. Why? Because of this data set scale, which is 0.5, is actually too large related to the curvature. But instead of exploding, it likely caused oscillation around zero direction with cancellation effects. However, notice something important. Initial loss is 15. Earlier with LR 0.1, initial loss was 14.57. Why different? Because different random seeds, or you regenerated the data, or you didn't reinitialize X or Y consistently. This matters in ML experiment. Case 2, small learning rate. Loss already low. This means something critical. You are reusing it. Well, you are analyzing it wrong. You are analyzing it wrong. How about I also, sort of print the LR value? Can I do that? I really want to do that, but nobody returns the LR value. So I guess I have to print it by hand. So I'll say LR is this. I'll say uh, print print, and then we'll directly in semicolons directly say that LR is this, and we print it. We get this result. We copy it. We paste it. Where are we pasting it? Over here. And because of that final loss, we say true weight. But before that, true weight, where are we printing? We are printing over here. I loss. Well, we are only going to 900. So if we go I sort of plus 1, if we get a different result like 1000. Ah, not plus 1. Damn it. Ah, Since 1000 is getting divisible by 100, this should happen, but it doesn't happen. Well, nobody knows why. What I in range of epoch? In range, it should mean equal to epoch, no? Does that not mean it? How does it equal to? Let's create a Python. If I say I in nine, I say for I in range of, let's say, 100, will it print 100? I don't think so. It will only print 99, but from 0. Uh, all right. So instead of saying, range, we should say something like this. Now this should make a change. It did. So let's first of all do this, and then we say semicolon. Then we say print print something like I. Will we see 100? We didn't see. So instead of saying, you know, this, we go like 1 to 100. Will I see some changes? Oh, not this. Yeah, damn it. No. So instead of, doing this all, or I say equal to 100, the range equal to 100. Will I get some? There is no equal to 100. So instead, we can directly say plus 1. Not here, but here. We'll say plus 1, and it will make the change. So we get 100. So instead of, whatever we were doing or were trying to do, what were we trying to do? I don't remember. But yeah, instead of doing this, how about I just go 1 over epoch, which is plus 1. Now I think we should get 1,000. Yeah, we get 1,000. We get 1,000. Now let's copy it. Let's let's paste it over here. Instead of saying 0.001, it is not this, it is 0.5, isn't it? Yeah, exactly 0.5. As for range epochs, well, plus 1 it, because we are not seeing 1,000, which we actually want to, because that makes a difference. It is making a difference. 893, stabilizing at like copy, and we go over there. We say something like break. We over there, paste. Yeah, and should take our real data and analyze it for real. As for epoch, just make epoch plus 1 everywhere. Everywhere. Epoch, we don't want epoch, we want epoch plus 1. Alright, we are epoch plus 1. Anywhere else, do we see epoch? Do we see epoch? If we see, well, just don't ignore it. It needs our help. Needs to be, well, plus 1. Epoch plus 1. Because that's how the range works. Somehow. Seems wrong? It is not. Because it starts from 0. What if it goes beyond, 1001? Now, what difference does it even make? Nothing. Where's the epoch? Where's the epoch right now? Oh, just tell me where is the epoch in range. It's so irritating. Find epoch. We are seeing everything except epoch plus 1. It exists over here, it exists over there. Yeah, it exists over there. Which is 1700. Good for it. Good for this. How about we replace it to 1000, so that we can get a uniformity. Are we getting some idea? Change positional argument to keyword. Hmm. I think it looks nice. It is nice. Everything is nice. Now what? Case one, 0.001, which is very small. So loss is, well, 15.169 to, well, decreased to only 15.1. Over here, we can see this. We can see this. It was earlier 15.16 and it only reduced till 15 point, 10 after 1000 epochs. So weight is something like this, 0.059, and then minus 0.0039, and then 0.0029. Yeah, this is exactly what we expected, and that's exactly what you actually got. But you are so stupid to understand. But all right, now update rule. Why update rule? So it is like wt plus 1, which is wt minus n and delta, ulta delta. Why is it upside down? And then l, if now n is 10 to the power minus 6, each step is microscopic. So after 10,000 steps, total movement is tiny. How about we make this epoch not just 1,000, we make it 100,000, we make it, well, something truly incredible that it thinks about and will be proud. Not this, not this. Underscore and how much is this? This is now 10 million. Let's make it a sort of near round about 100 million, and let's run it. It will take much of a time, but we'll be sending that time over here. So let's see over here, and we shall just go to the down next. Let me possible. Oh, yeah. Now we see that each step is microscopic. So after 1,000 step, total movement is tiny. But after 12,000, it is not, because it is decreasing, not gradually, but, well, gradually, but still we are seeing that decrease happening live right now. So after 1,000 steps, total movement is tiny, gradient descent is working correctly, just extremely slow. Now this confirms that implementation is correct, optimization dynamic behaves as expected. Case 2, which is LR, which is learning rate, is very high, 0.5, which is large. Now interesting, loss immediately nearly optimal. So let's go and see that loss also. So where is this? Yeah. So loss is nearly immediately optimal. It is not starting from 14 and all that. It directly goes from 0.01, well, then stabilizes at 0.01003, which is directly the second step, not second step, after 100 epochs. And from 200, 300, we are seeing the same thing. So this is surprising at first glance. Why does the large LR not explode? Because this problem is extremely well conditioned. Only three features and random Gaussian feature, and X transpose multiplied by X has small eigen values. I don't know what that means. Eigen, and noise is small. Quadratic bowl, which is nicely shaped. All right. And in such a simple case like it's 0.5 is still below instability threshold. So convergence happens extremely fast, essentially in just one step. That is why epoch 0 is already very small loss, obviously. Compared to 14 and all that, it is very small loss. And compared to that 15, well, yes. Now, epoch 0 is already very small. Important is you are observing the effect of curvature scale, which, like, learning rate stability depends on the lambda max, which is like wavelength of max, and then X transpose and X matrix multiplied together. Now, not an arbitrary intuition. Learning rate depends on this. And what is this? Don't know. Is lambda the wavelength? Wavelength of what? I don't understand. What is this lambda? Now let's go deeper, which is optimization theory. So recall the stability condition, which is like this. Well, I can't recall because I don't even know that. So recall the stability condition. All right. Since it said so, we are assuming it that it is. Now lambda max is small, then even n, which is 0.5, is safe. If features were scaled 100 times larger, then n 0.5 would explode. And this is why feature scaling matters in ML. Now, critical concept question. Suppose we multiply all features in x by 100. So if there is a x earlier, then we create a x new. What happens to the gradient magnitude? Equivalence of x transpose x. Maximum stable learning rate. Think carefully, answer step by step. I don't know. Should it explode? Well, let it finish first of all, the 100 billion one. And next concept is conditional numbers. So earlier I asked, why does convergence speed depends on? What, eh? What does convergence speed depends on? Either it should be like this, or why does convergence speed Ah, why does convergence speed depends on this, which is lambda max upon lambda min. Here is a geometric intuition. So loss surface is an ellipse, which is k is nearly 1, which is circle-like. So fast convergence. If k is large, then long narrow valley or zigzag behavior or slow convergence. Now explain it in your own words. Why does elongated curvatures causes slow convergence? Use geometric reason and system questions. If feature increases from 3 to 1000, x becomes something like this, which is 100k, which is 100,000, and this 1000, and this is the shape of x, which is matrix x. What happens to the memory footprint? Cache reuse and computational per epoch, risk of ill conditioning. Answer carefully. We are transitioning from coding to optimization geometry and system scaling. Stay precise. Okay, 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 okay. I don't understand. Starting, starting from here. What is lambda doing here? Is it way? Am I stupid? Is is it a way? Then paste everything. I did. Let's go on. And our program, which was over here, is still running for past 7 minutes. Let's go and see where did it reach, or where is it trying to reach. Well, oh God, my CPU is right now burning up. It's 99% getting used, 97. Damn it. Since it's running on, Google Colab, why is my PC burning up? Damn it. And my RAM? RAM usage is near only 24%, 25% because I have 16 GB RAM and only 4 GB is getting used. So even if I had something like 8 GB RAM, that would have been sufficient. Well, it touches 99 most of the times. So let's see HTOP right now. What's happening? See, this is our core. It is like build, and we are seeing something like 408 threads, 97 tasks, 117 kilo threads, or I don't know, THR means threads or throttle. What does it even mean? Four load average, three load average, four, three, and all. Let's magnify it. We have two. Let's go with there. So let's shift it to three. Let's make it V. Let's see. Well. CPU is mostly used by, Brave, which is very brave to even use my CPU to 75% alone. And my OBS is already taking, mostly sort of 50% almost user bin OBS. So that's for recording. My Hyperland and Stop is only taking, well, minimal. So like 5.2, like normal. Not very normal, but still normal. Uptime is 13 hours. Well, it is. Oh, damn it. It shows. Nah, not damn it. It shows real, right? Like it is only using 3.54%. I saw these, yellow lines and I thought it was near sort of, but only the, these green line matters, which is only 3.55 gigabytes. Swap, well, no swap is used because it can't even use my damn RAM right now properly. What can it even do with my swap? Uh, so I think it's speeding up badly. Let's close this so that we don't create more ruckus. Ah, it has not even reached sort of, half a million. No, it did. It did. It did go beyond half million. It's near 3 million. So let it burn. Till then, we learn about all these theories. So let's learn about theories. Mhm. Well, now is the stage where my CPU or my computer is freezing up. So no multitasking and all that. My CPU is literally freezing up. Yes. See, I need a powerful machine. It's not like I want, I need it. So no, lambda is not wavelength here. This is linear algebra, not physics. So we reset cleanly and build from first principle. What is lambda here? We are talking about x, t, and x, which is x transport multiplied by x matrix. So now this is a square matrix of shape d comma d. In your case, d is equals to 3. All right. So we get a matrix of 3 multiplied by 3. So 3 rows and 3 columns. What are eigen values? So for a matrix square, for a square matrix A, the eigenvalue lambda satisfies something like this. So AV is equals to lambda V, meaning V is the direction, lambda is how much A stretches that direction. So X transpose XV is equals to lambda V, whereas A is our square matrix. We are getting from X transpose X. All right. So means if we move in direction v, the curvature scales by lambda. And step two, why do eigenvalues matter for gradient descent? So linear regression loss, which is LW is equals to 1 by n xw minus y to the whole square. This is a quadratic ball. Its curvature is determined by h is equals to 2 upon n xtx. Now the h is called the Hisen or Heisen. Now the eigen value of x transpose x tells us how steep the ball in each direction is. So quadratic is something like this now. So it's telling us if it's standing ball, if it's wide ball, something like that. Step 2. Why do eigenvalues matter for gradient descent? So linear regression loss looks something like this. Now this is quadratic ball because of square. Now its curvature is determined by this. Nice. Now this is called a Hisen. The eigenvalues of xtx tells us how steep the ball is in each direction. A stability condition for quadratic problems, the gradient descent is stable. So for quadratic problems, the gradient descent is stable if 0 is less than the n less than 2 upon lambda max. The lambda max is largest eigenvalue of xtx. Why? Because largest curvature direction is not is most sensitive. If step size is too big related to curvature, you overshoot in that direction, which is oscillation or divergence. Now answer the feature scaling question. Suppose x nu is 100 times the x. What happens to the gradient magnitude, which is gradient something like this? So x is 100 times this. So it becomes 100x. Now xw becomes 100 xw. So xt becomes 100 xt. Now everything is getting multiplied by 100. So approximate dominant term, which is gradient scale, roughly scales by 100 to the power 2, which is 10,000 times. So gradient magnitude becomes 10,000 times larger. What happens to the eigenvalues of it also becomes 100, 10,000 times larger. So all eigenvalues scale by 10,000 times. What happens to maximum stable learning rate, which is n? So this n, which is not n, which is something like nu or something like that. No, snu is u or something like that. N is what? There is lambda, and this n is used for frequencies. It is called what? Or whatever. We'll call it just a long n. This is something called like n in Greek is, what is it? Mu is something else. Do I have my phone right now? Uh, so it's nearly, going to be 12 o'clock very soon. So I'm going to just stop recording, or will just end my day after, completing this Python somehow. That's what I'm trying to achieve. What is n in Greek? Yeah, so n is new. No, this is v. So n is what? Not new. New looks something like v. But I am not talking about new. I am talking about, the real doppelganger of n. What is it called? Eta. Eta. Uh, what is n or eta in Greek? So yes, this n is called eta. Uppercase looks something like h, whereas lowercase looks something like this long n. It is called eta. All right. So I think we should move on. So the stable learning rate is represented by eta, which is long sort of n, which is this. This is eta, which is long stable learning rate. And if it is less than 2 divided by, lambda max, which is x transpose multiplied by x, what is it actually called? X multi lambda max, which is eigenvalue. All right. So I think this lambda becomes eigenvalue, and this becomes a stability, and stability what? Stable learning rate. All right. Then the maximum stable, the eta becomes 10,000 times smaller because it's indirectly proportional to the lambda. If it becomes 10,000 times larger, this becomes 10,000 times larger, uh, which is in denominator. So this numerator, which is inversely proportional to this, will become 10,000 times smaller. So if before n is 0.5 was safe, now it must be 10,000 times less to remain stable. This is why feature scaling matters. Now condition numbers, which is like k, which is kappa, I guess. No, k is kappa. Let's search it down. When it comes down to that, we should just search it. K is kappa. Hmm. Yes, I see that K is a kappa. So the condition number, which is K, which is kappa, this measures how stretched the bowl is and why does large K causes slow convergence. Imagine if one direction which is very steep and one direction which is very flat, the bowl looks like long narrow valley. Now gradient descents. So takes a large steep in steep direction and sorry, takes a large step in steep direction and small step in flat direction. This causes a zigzag pattern because to avoid exploding in steep direction, it must be small. This eta must be small, so that the small eta makes movement in a flat direction extremely slowly. Thus, the large kappa shows convergence. This is geometric reasoning, which I don't know about. So I'm learning right now. Now, system scaling question. If features increases from 3 to 1000, now X shapes become something like this, which is very interesting because instead of 3 we now have 1000. So this matrix is now 100,000 multiplied by 1000. 100k multiplied by a k. So memory footprint becomes something like 2.4 MB, but instead of that it becomes 800 MBs. One step. This is just one step, one epoch, I guess. Now the cache behavior. Before, like previously, entire matrix could fit into L3 cache easily. Now matrix far exceed the cache. So more DRAM should be accessed, more DRAM access, lower cache reuse, and more memory bound. Now computation per epoch, which is matrix vector multiplication, which is constant, which is n into d. Before it was 300k multiplications, but now it is 100 million multiplications. Damn. So computation per epoch increases. So I think this computation, which is lower for per epoch, will become insignificant. But instead, for just one epoch, it will take so much damn time that we will have to, do some less epoch. Like right here, I am going near about, 6 million. And there is, losses are reducing faster and faster, and it's becoming stable and stable. Even if the learning rate was like 10 to the power minus 8 or something like that. I don't remember exactly. So more DRAM access, lower cache reuse, more memory bound. Computation per epoch becomes like costlier. Before it was only 300k multiplication, but now it is like 300 times more. Now risk of ill conditioning. So with more features, feature may become correlated and XTX becomes nearly singular. Now lambda min, which is becomes very small and kappa becomes large. Now convergence becomes slow and unstable. Now testing understanding. If we normalize each feature column to have mean 0 and variance 1, what happens to eigen values roughly? Why does this improve training stability? Now what I think is, uh, well, today let's close our day with revision of all the concepts that we just got learned and were PAUGST in this day. Why? You must be asking. Because too many concepts in single day will cause me to forget them easily. That's why. This has been running for 25 minutes now. Well, that's some dedication over there. Good decision. We consolidate, no new material, only structural reinforcement. Today, you move from vector operation to optimization geometry and system scaling. Let's compress everything into a clean mental model, which is part one, linear algebra core, which is dot product of A and B. Then we saw that we added AI, BI, meaning weighted sum, fundamental ML primitive, and used in predictions. Now, system insight, Python loop, which is interpreter overhead, and NumPy, which is contiguous memory plus SIMD plus C backend. And memory bandwidth often dominates the arithmetic in terms of, you know, bottleneck. Matrix vector multiplication, which looks something like this: y is x, and then this is w, which, well, it looks like a w, but it is not. It might be omega, I think, but since it looks like more like a w, so we'll just assume it's a w in a cursive. Ah, so shape is like nd, which is number of, which is 10, 100k, and d is sort of features. W is again the feature, and nobody knows how many column are there. We see something like 100k and 3. Now w was 3, and xw, which is now multiplication of these matrix, we get n, and d gets cancelled, and this empty thing comes to our xw. We multiply it. So shape, we now have a clear understanding of how the shape of all these matrices would look like. All right. Now interpretation. So each row is one data sample, and each column is one feature. So prediction is equals to combination of features. Weighted combination of features. So part 2 is loss and optimization. Mean squared error. So this is for a mean, which is 1 by n. The summation is summation of our errors. So how many errors are we getting per n? That is what mean squared error is. Y squared penalizes large error. So if there are large error, it penalizes, it makes it more magnifying, more enormous than it is. So that's why. So differentiable, it is convex for linear regression. Regression. Now gradient, this was gradient. Ulta triangle, this was gradient. Upside down triangle, upside down delta. What does that mean? Well, we don't know for now, but it means gradient. And why do we get 2 over here? Because the squared, which was obviously here, after differentiating, it comes up over here in multiplication, and 2 minus 1 becomes power of 1. So it gets a power of 1. As for, we get another thing, which is X transpose, which is nothing but a matrix of uh, just the size of dash comma n. It becomes the opposite. Like this is n comma and let's say dash, which is empty, and it becomes opposite like dash comma n, something like that. All right. So now we know gradient. We know x w minus y is residual vector. All right, which helps in sort of prediction. You know, it did help in prediction, predicting a lot of things. No, no, no. I'm getting something wrong. It means, error, not prediction. What is prediction? This is prediction. But this is matrix vector multiplication. So, all right. Now, because of all these concepts, we are getting sort of confused, but no need to, because we'll be seeing that often from now on. Xw minus y is residual vector, xt, which is aggregates error contribution per feature. Key structural idea is gradient is direction of steepest increase. We subtract it to descent, and gradient descent updates look something like this, which is w minus n, and this delta, which is not delta actually, but it is gradient. So gradient times eta minus, this omega or w is the new w. Now n or the eta is learning rate. We are multiplying gradient to it and subtracting from the w, which is like the true w. We are getting a new w for that. No, w is w, not true w, right? Now too small, slow, which is too large, oscillation or divergence. Proper is smooth convergence. So if it is too small, learning rate, if it is too small, then it is very slow. Right here, you have to go over how many, nearly 10 million epoch to get somewhere even near 2.9999. So too small, then it becomes too slow. If it is too large, then it oscillates or starts to diverge. If it's proper, we get a proper convergence or a smooth convergence. Now, part 3 was the geometry of optimization. So loss surface of linear regression, which was quadratic ball. So curvature was determined by x transpose x. Now eigenvalue looks something like lambda, and lambda max is steepest direction, which means the steepest to the respect of y. If it is very close to y, then it becomes the steepest at 90 degree. If it is little bit like 85, 80, 75 and all that, it becomes that steep. So all right, so if lambda max, then that is the steepest direction, and let's say it goes like something like L curve, but more smooth, something like this, L curve. All right, so the L surface, or the first left side surface, is like max, and then the flattest direction, which is L, the rightmost surface, which is flat, so that is lambda min. Well, yeah, that's quite intuitive. Like, see a normal L, well, a capital L. Uh, See, this one, the leftmost corner from here, it is very steep, whereas this right one is very not very steep, just a flattish direction. So if you were to walk on this L for steep direction, you have to walk slowly. As for the fastest or the flattest direction, well, since the step is very slow, you still have to walk slowly. Now, stability condition is that 0 is less than or eta is greater than 0, which is less than the 2 over lambda max, which is steepest direction. So if lambda max gets 10,000 times bigger, the eta decreases or gets smaller than 10,000 times. Large delta max must reduce the learning rate. If this is not satisfied, then it might explode. So large lambda max should or must reduce learning rate. If it doesn't, everything explodes. So now condition numbers is like kappa, which looks something like this. So we have lambda max divided by lambda min. If kappa is 1, that means we have a circular bowl, something like near O or U. U would be a great example of circular or near circular bowl. All right, over here. Now, fast convergence, if K is large, then narrow valley, zigzag, or slow convergence. And part 4 was feature scaling. So if x new is, let's say, 100 times the x, then the gradient scales to 100 squared and eigenvalue scales by 100 squared. Stable learning rate shrinks by 100 square. Why? Because this is eta, and eta is inversely proportional to the lambda. The lambda, which is eigenvalue, isn't it? Lambda is the eigenvalue. All right. So now we know eigenvalue scales by 100 squared, then stable learning rate shrinks by 100 squared. Now that is why the feature or normalization matters. Part 5 was system perspective. So as D increases, memory grows O over ND, and then compute grows over O over ND, and catch reuse decreases, ill conditioning risk increases, and full batch training becomes memory bound, which is RAM bound. So the faster the RAM, faster you go. Good. Now part 6, memory versus compute. So we learned arithmetic is cheap and memory movement is expensive. Now dot product often, memory bound is often memory bound. So creating intermediate array increases the memory traffic. Contiguous memory enables SIMD. So strided array reduces the vector efficiency, and that's enough for part 6, which is memory versus compute. We learned if arithmetic is cheap, memory movement is expensive. Why? Because we have large matrices and all that. We have to move them for dot product and all that. So dot product often is memory bound. Creating intermediate array increases memory traffic. Contiguous memory enables SIMD, whereas if it is scattered over, we can't use SIMD. We can't even vectorize it. And what else? If it's scattered, we can't vectorize it. It can't be loaded into CPU cache. So yeah, no CPU cache loading. Now, strided array reduces the vector efficiency. That's what I was talking about. Reduces the vector efficiency, and the CPU caching gets disabled, or you can't just use CPU caching everywhere. So no SIMD and all that, because there is no vectorization. Vectorization is not possible. So part 7, what you actually built today, you implemented a manual dot product, good for us, and directly jumped to NumPy vectorization comparison, and then matrix vector multiply and full batch gradient descent and learning rate experiments with LR. We are still doing it, and it's still going on for, well, near 40 minutes. Good for us. and learning rate experiment, convergence behavior analysis, yeah, something like L shape, U shape, and all that. Feature scaling theoretical reasoning. If we scale the future, if we scale the future, not future, if we scale the feature, well, yes, by 10,000 times, then our matrix size, instead of becoming from 3, we get a of W, it becomes from 3 comma dash to becomes 10,000 comma dash, and our X matrix also becomes something like 100,000 comma 10,000. So it sort of increased 100 times. So if our matrix X increased by 100 times, our matrix X transpose also increased by 100 times. So that resulted in being a resultant increase of 100 squared. Now, if Xgen value increases by 100 squared, our what eta, which was what, which was learning rate, should or steeply decreases by 100 squared. Now, this is in my mind. I was recalling it, or sort of actively recalling it. So now that's in my mind. Let's see for how long it stays there. Now we understood convergence behavior analysis, full scaling theoretical reasoning, sort of feature scaling. Yeah, features, not full. Yeah, feature scaling theoretical reasoning, absolutely. System level scaling analysis, I don't know. And I don't care for now because I don't know. Now this is not beginners and ML. Well, it doesn't look like this. For past, I don't know, day 6, we were just benchmarking a damn NumPy versus Python list. And at day 7, it suddenly exploded into not being a beginner machine learning level. We couldn't even, follow some Rust or do something with Rust. Oh my God. Now, final check is no coding, answer briefly. Why does normalization improve gradient descent stability? We are talking about the upside down triangle, gradient descent stability, or over here, the train function. Why does normalization improve? I don't know. What is large condition number? Why is large condition number harmful? Well, it can explode if you don't, make the learning steep, learning rate go below that, and the size of matrix also increases, so the chances of being harmed increases. Why is memory bandwidth critical in large scale ML? Answer those, then we close the day with your clean lock. I'll answer, I don't know. I don't know clearly, but I sort of have an idea of it. Now what? Now what? Good. That means we must clarify and not move forward. We close day after only after clarifying. So let's compress each idea into something concrete and intuitive. So why does normalization improve gradient descent stability? Suppose one feature ranges, which is feature A, values around 1, and feature B values around 10,000. Then gradient contribution from B will be huge, and gradient contribution from A will be tiny. Yeah, because of 10,001. So loss surface becomes stretched. One directional very steep, one direction very flat. Becomes L-shaped, isn't it? Or near L-shaped. So that means that lambda max becomes large, lambda min becomes small, condition number increases, eta, not eta, kappa increases. So conditional number increases. What was kappa actually? What was kappa? Where's kappa? Where is kappa? Oh, so kappa is condition number in itself. So k is near 1, then circular bowl, and fast convergence, k is large. If k is large, so greater than 1. No, k cannot be greater than 1, no. Because k is ratio between 0 and 1. So 1 is the largest it can go. All right. No, that's not possible. Like k can go large. Why? Why? Let's say lambda max is very, steep. Lambda min is not very steep. What it does? It does nothing or approximately nothing. Not even halving it, something like that. It might, it might not. That all depends. Now it is still not done, still running. So I think I will not use my whole damn compute for this. I am going to, just change the runtime so that I can stop everything at once. We'll create a TPU. We are not saving anything. Disconnect and delete runtime. Yes. So, well, because it's still going on and, well, was running for I don't know how many minutes. Now what we'll do is we'll close this for today. If you want to read these answers, we'll read it. This becomes condition number increases. Result is that you must use tiny learning rate to avoid exploding in steep direction, that we know. But learning rate makes flat direction move slowly. Yeah. Normalization mean is zero, variance is one, makes future scales comparable and all that. Why is large condition number harmful? If K, whereas kappa is large, loss surface looks long thin valley, so it must go very slowly. So this causes slow convergence and zigzag trajectory. Geometric picture is like whatever. This is why it's memory. So we repeatedly do something like x multiplied by w. So for large x, every epoch reads entire matrix, and that is massive memory movement. So compute is cheap, data movement dominates, and all that. Bye bye. All right. Just create the damn log. All right. Bye bye. This is it.